Second for him. First time, in person, and then straight to this one. Oh, yeah. Can we change the presentation to PDF because welcome to change the PowerPoint? It's yeah, fine. It's all lucky. Can you guys help? Namen sind Ich habe ihn gesehen.
Ja, was heißt es?
Ja.
Ist das schon Salzzeit?
Ja.
Ja, seid auf
So background is set. That's your name and credentials, and PowerPoint is already online. You can start and switch with these.
Okay, are you fine? Just want to look at the screen. Is that okay for you?
Yeah.
Yeah.
Yeah. So I think that was going right. Yeah. You have also laser and the slides. And here, just unfortunately, the smaller room, it's not equipped with microphones. Okay. Like this one is online for the broadcasting. Yeah. This one is for the room, but you need to be a little bit closer. Yeah, yeah. So I need to stand there. Yeah. For the audience online as well. We can set it up.
Work with Tim?
Yeah.
Nice.
You know it?
Yeah, he's a good friend of ours. Yeah, so I was in the facade research group for quite a long time. I did my PhD in 2014 with him also.
Yeah. Yeah, so I'm first research now.
Okay. Okay, cool. Nice.
Soll das Licht ausschalten?
Das Licht? Ja, super. Nee, wir stellen einfach nur das nach. Ja.
This is the camera. Yeah. Yeah. How do you spell your name?
Pronounce your name?
Yeah. Immer zwei. Ah, ja.
I don't know anyone this person. It's my love later. I do it. Was hat er Vormittag? Jemand von den Energy heute? Okay.
Dann müssen wir.
Das Signal ist, ich glaube, nee, eigentlich ist es ein globales vielleicht mal jetzt halt mal.
Brauchen Sie Mikrofon? Also der ist über ihn da eingestellt, vielleicht noch ein. Ja, ist dann. Der Hausmeister wird uns verteidigen heute Abend.
Ich glaube, wir können die
Er ist auf unserer Seite.
Ja. Das ist schon mal. Aber ich glaube, wir können die auch eher rennen. Also, das hier kein Problem sein.
Ja.
Schon.
Guck mal, was der genau.
Guck mal, der hat nichts.
Das nicht nehmen, weil ich habe immer diese Programme.
We go to the Q&A session. Und dann am Rest of people will take place da. Das heißt, die können schon um 6 hier sein.
Okay.
Können um 6 in diesem Raum.
Sind wir online? Ja, aber den Code kann man erst nochmal muten, solange wir jetzt.
Achso,
Heute kam so ein Rückmeldung
also
von meinem Team. Die ganzen,
Der ganze Raum.
ja. In der Minute. All right. So welcome to the energy session here in the room 2. My name is Jens Schneider, and I'm going to lead you through this session. We do it that we do 3 presentations in a row, and then we will have a Q&A session afterwards. And also we will collect, I believe, questions from online participants. Welcome also to everybody who's online. I hope everything looks fine with the mic and the camera. So our first speaker in this session is Stein Kracht from TU Delft, and he will present work on retrofit window films for energy efficient building renovations. So Stein, please.
Hi. So let's see if everything works before we start.
I just got it for a second. Thank you.
Other one.
Yes. Oh, that's the wrong one.
Yeah, so my name is Stein Kracht. I'm a postdoc researcher at the university in Delft. And I'm also co-founder of the startup PowerSKIN Technology. And yeah, I'm happy to tell you about the window films that we developed in this project at the TU Delft and also at the company. So these days, over the past decade actually, more and more people move to urban areas and live in cities. And in these cities we consume, of course, a lot of energy. And when we zoom in on the buildings, then we consume 36% of the worldwide energy consumption in our buildings. And of this 36%, over 40% is used for heating and cooling of our spaces. And over the past years, we have been able to decrease the amount that we need for heating, mainly by insulating also our buildings properly. But we see a trend that the energy used for cooling is increasing. And it's also seen here. So this year we consume about 3,000 terawatt-hour of energy each year on cooling our buildings, and that it's expected to increase over the coming decades. And also we see this in European buildings, more and more air conditionings are installed in houses. And this of course has to do with the rising temperatures and periods of longer warm temperatures, but also with the amount of glazing that we use, and the amount of glazing that we use in our building. And yeah, glass plays an important role in the energy efficiency of a building. So, for instance, in summer, 60% of the solar heat gains that are coming into our building are actually through the glass. And then we are talking about the solar radiation that is the UV, visible, and near-infrared light range. On the other hand, in winter, 25% of the heat that's inside our building is leaving our building through our windows. So now we are talking about the long wave radiation that is getting out. So by insulating our glazing well, we can keep in the heat in winter and save energy on heating, which is of course a good thing. But at the same time, we create a problem in summer because all the heat that's getting in is not able to get out. So this also enhances the need for cooling more. And the idea is that at some point we will need a combination of insulation with good solar heat rejection to keep our building environment comfortable, temperature all year through. And this need to renovate buildings is also recognized by the European Union, which states that 35 million buildings have to be renovated by 2030. And if we focus on the glass and upgrade all the glass in our European building stock, we can save 29% of energy use each year, equaling 94 megatons of CO2. So yeah, there's a lot of room to improve in this area when we focus on the glass. And to anticipate on that, we are developing window films that are able to reject solar heat. So they keep the heat from outside, from the sun, and reject it back. And we have films that we can laminate between the glass, which is more an application for new glass constructions. But we are also developing films that can be applied as a retrofit afterwards, so on existing glass and existing buildings as a renovation option. So there are different types of films that we develop. We develop films that permanently reject solar heat, which we call static window films. There we have two versions, one that is color neutral, but we can also implement some color to generate a more decorative effect. And on the other hand, we are developing adaptive window films which respond to the environment, to the outdoor weather conditions, such as sunlight intensity or temperature. Today I would like to focus on on static window films and the photochromic window films. So let's start with the color neutral static window film. And this film, as the name suggests, it's very transparent. So it looks like a regular window. Have 88% of visible light going through when it's attached to a single glass. But at the same time, it's able to reject 21% of solar heat. So without being seen, it still rejects a considerable amount of solar heat. And the reason for that is that this film is able to reflect light of a specific wavelength, in this case around 900 nanometers, which is invisible to the human eye. But it's heat that is in the solar radiation spectrum. And this technology that we use Next slide I will tell how it works, but we can also very easily tune it to different colors, such as red or green. Then you generate a more decorative effect. And then you see also the reflection is in the visible light range. And this color is angular dependent. So if you pass by this glass facade, you will see change in the color of the glass, which gives a kind of an additional design option to an architect to play with color. And it also leaves indoor, it leaves a little bit of outward light ambience. So the wavelengths that are transmitted is the color basically that you see inside, which is in this case quite a subtle color change. So I promise you to tell you how it works, so this is what I will do. If you zoom in on the film, then it's composed of several layers. And one of these layers is a reflective coating that is developed by current technology. And in this coating, there are molecules. I will not tell too much about technical details because it will probably bore you too much. But this is what we call a allosteric liquid crystal. What you need to, what you can remember, that these molecules are able to organize themselves in this kind of helix structure. So we coat a single layer, and then the molecules tend to organize themselves in this particular fashion. And because they organize like this, you create differences and refractive index throughout the coating thickness, and therefore you can reflect a certain wavelength of light, which is dependent on the length of this helical structure. On this length, we can very easily tune with the composition of our coating. So if we, therefore, we can very easily either reflect in the near infrared region or reflect in the visible region and the color. And this technology, we were also able to scale up to a certain extent in a continuous roll-to-roll process, so it can read this length, in this case 20 centimeter wide, which of course at some point we also need to widen further. And we did this together with a company close to Düsseldorf, Dormagen. So for this system, yeah, we will also set up a pilot study to see if it works in the real environment as well. So I hope you now have an idea of how these static render films behave and work. But I would also like to draw your attention to the photochromic render film. It's a different technology, so it responds to sunlight intensity. And what it does is when we put this film outside in the morning, it is transparent, but on a sunny day, when the sunlight intensity increases, the film gets a certain tint, and when the sunlight intensity decreases, it becomes transparent again. But it is not only changing in the visible region, as you can see here, but it's also changing in the near infrared region where we cannot, which you cannot see, but which is the heat sun. So there is a change in the visible light transmission from 83 to 48%. But at the same time, this value, the solar heat gain coefficient, which is basically how much solar heat is going through your glass, is also reducing from 0.79 to 0.49. So from 21 heat rejection to 51% heat rejection. And this film, the first prototype that we made, which is the blue curve here, we were able to have very fast transition from the transparent to the tinted state, which was within 1 minute. But the reaction from the tinted state back to the transparent state was very long. It actually took 2 days to come back, which is of course too long for practical applications if you want to switch within 1 day. So with some chemical modifications, we were able to reduce this to about 20 to 40 minutes, which is also the reason why it can switch within 1 day between the tinted and the transparent state. So this film has basically two main advantages, and this is one is the daylight comfort, so it reduces a little bit the daylight that is coming in when the sunlight intensity is too bright. It also cuts off annoying glare at these moments. But the other benefit is the energy efficiency of a building. For that we did simulation work with design building. We have this model, this office space with offices all around. We implemented low E glazing with a good insulation value, but lacking the solar heat rejection. And then we applied to this glazing a film that permanently rejects the heat, so as if the photochromic film is permanently in its tinted state, and compare this to the situation where we have this photochromic film with the adjustable transmission. And we did this for 4 different climates, so 2 warm climates, one Guangzhou, which is in the south of China, and Lisbon in the south of Europe, and Amsterdam, of course, in the Netherlands, and Beijing. And you can see in all these climates, you reduce the amount of energy that you need to cool your building, which is because you are rejecting solar heat, so you need less energy to cool the space. But in a climate where you have distinct summer and winter, such as here or in Amsterdam, Europe, at least Northern Europe, and you need to use your heating in winter, you see that with a permanent solar heat rejected film, you need additional energy to heat up your space. And it is because in the winter months, when you reject the heat, you need additional energy to get your room warm. And this is less the case when you use the photochromic film, which is able to adapt, because in winter, this photochromic film is, the sunlight intensity is generally lower, so the film is in its transparent state, and therefore allowing the heat to come in more percentage of the time. And this makes that for Amsterdam, when you use the permanent heat rejection, you need actually 3% extra energy to keep your building comfortable. While with photochromic film, you can save 18% of energy. I would do a quick calculation with installation costs of this film of about 32 euros per square meter. And the current energy prices in the Netherlands, I don't know how that relates to here. But then you come at a return of investment of 5 years. Of course, these numbers are a bit changing all the time nowadays, but it gives you an impression of the potential of this kind of film. With that, I would like to conclude. I hope you enjoyed and you've seen how these films work a little bit and the different types of film that we are developing. I also have prototypes of these films with me, so if you want to see them in action, just catch up with me during the break and I can show you. And we can discuss a bit further. And we also have a special paper in the Journal of Facade Design after this conference, which is about the energy efficiency of the static render film and the thermal render film. If you're interested in that, please have a look. And with that, I would like to thank you, and also the people online, and I'm happy to answer your questions.
Thank you. Thank you, Frank. We can do the Q&A session after, because we first want to go through the 3 presentations and then we collect questions. You can come up to stage again. Okay. So the next one, as we are a hybrid conference, is somebody in the virtual room. I hope at least waiting for us. So this is Peter Simmons from Library. And I don't know if everything is fine on the Yes, correct. Thanks, Peter. Very good. You made up. Yes. You made up a lot of the time. And I don't know where the noise comes from now.
Das Mic aus und hier rüber sprechen.
Okay, I'll try like this. So we had some problem with the mic. So it's yeah. We have an alarm here. I think today is in Germany it's alarm in all the buildings. That's why there's the noise, but it's only a test alarm. So anyway.
It has nothing to do with the microphone.
No. Okay. And we will come back to you, Peter, then for the final Q&A session then after the next presentation. Yeah. Yeah, it's a test alarm. It's in all of Germany today. It's just test. Good. So now we come to our next speaker. It's another online presentation. It's Akash Shanglani from TU Delft. And the topic is facade delete, facade optimization for visual comfort by controlled daylight distribution in high-rise office buildings. And I think, Akash, you're online now. And it should work that you just share your screen then. Let me put this on here. Yes, we hear you. Yeah, but you have to share your screen first. No, we cannot. We cannot see your screen now. We only see your camera picture from. We see basically your face. So maybe you have to look on your sharing mode that you go to the. Yeah, now it starts. Yes. Yeah, just now it shows. Yes, perfect. Thank you. Well, thank you, Prakash, for that presentation. Now we have a Q&A session. Just start the sequence that we have. Online, so maybe check on chat. Here live. I start with one question. Sometimes stand so the small so das your check that. You can have a look if this is from the on. So we have these two mics here. This is the better one. It's this one. Okay. This one.
The we are reflecting around 900, quite a large density. So that's 21%.
Probably. But then still this application is more its own surrounding. Today, like to have gains. It's summer.
We've calculated that when you combine it with our engine, then you still have a benefit. Somewhere that combined with the glazing or double glaze, right? Add it in, they then are
That's the comment. More questions? Jeremy had things beforehand. Change the counting. So, maybe to of course, this static situation. And I'm curious about the rebound effect because if we sell that to people, they put it into the window. Maybe they don't have a cooling device, but of course they have a heating device that is economic.
Yeah.
And then we increase heating even if they didn't want to.
Yeah, let's split this up into the different questions. I think the first one was about the low E coating, right? Yeah. There are actually companies that try to make such films. So larger players in the field, but they faced some problems. So the durability of these films was a bit lacking because these low E coatings over time they get this kind of discoloration when you do not protect them. So these, yeah, at some point they get them out of their portfolio because they were not, yeah, they lasted for 8 months, and then you had to peel the film off, which was of course not the intention. That's how it be. And yeah, for us, so this project started with my PhD research that I did at the University in Eindhoven, where so I have a more chemistry background where I developed these reflecting materials. So yeah, because we saw it was kind of difficult for these larger companies to make low-E films. Yeah, and we had the technology for solar heat rejection. We went into that direction. But yeah, low-E film, if that can be made, that would be a very good solution as well. Yeah. Yeah, now you have to remind me of the second, third, and fourth question you have.
The durability.
Yeah, durability. So these films, our ambition is to apply them on the exterior of the building, so they will face yeah, weather influence from rain and sunlight, of course. So there is we are developing our protective film that goes on top of our coating, and we aim for a lifetime of 10 years. And yeah, after these 10 years, film can be peeled off from the glazing. So you have the original glazing back. And we are also looking at how we can yeah, regain the materials that are inside the film to make it a circular product as well. So yeah, 10 years is the concrete lifetime to your question. And yeah, for the adaptive, you're also asking about the adaptive solution, right?
I was considering maybe a loop effect because it's then applicable to amateurs, and they just put it in their window even though they don't understand because the window is very sensitive. You know?
Yeah. No, indeed, you cannot just apply any film to any window, because there is yeah, if you create thermal stresses inside the glass, and there is a risk that the glass will break if you do not install the film properly. So if you, for instance, put the film on the inside with a low-E glazing, you indeed get heat generated inside this glass. So usually these films are installed by professional installers who know in what situation you can apply what type of film. But for this film, if you apply it to the outside, it's reflecting heat away. So the glass itself, so there's no absorption, so the glass itself will not heat up in this case. And there's also no chance basically on thermal break of your glass.
All right, thank you. Just maybe we go to the other one, but maybe you stay here and then more questions come. Other questions to Peter's presentation on the infiltration and exfiltration. Maybe Peter, if you're online now, I have one. I didn't fully understand. Do you also consider the updraft effects in your calculations? So the updraft effects in such tall and megatall buildings that exist through the elevator cores and this, because from my experience, this also has significant influence on the question where we have infiltration or exfiltration. Is this considered in your calculation? Peter, is Peter Simmons online? It's difficult to hear. Okay. All right, but maybe then we have to, maybe you stop the Zoom here. Is it better? Is it better now? Yes. My question was the effect of the updraft you know, you have the updraft effects in the buildings, which from my experience have a big influence on the exfiltration, infiltration problem, depending on the conditions. Is yeah. Yes. Yes, exactly. Because I mean, that's why I'm asking, because my experience is that if you have a updraft effect in the winter, and then you have a relative humid air from the building, and it's being collected in the upper floors, and then you get exfiltration, and then sometimes the double facade gets a lot of moisture. And these effects, this is extreme. These effects can be much stronger than envisaged by it, floor to floor effects. Yeah. Yeah. Yes. Yes. Very good. Yeah. We need a system approach. Um, more questions on Peter's presentation here from the audience, or do you see from the online?
So far.
So far not. Okay. Maybe then we go for the third presentation for the moment, which was by Akash about the facade optimization by this controlled daylight distribution. Other questions in the room or in the audience online to the presentation by Akash? Yeah, there's just wait. I tried the mic. Then we see if it works.
Hello, my name is Michelle from University of Alberta. Thank you for the presentation. Actually, I have two questions. One regarding this optimization process. Is it possible to explain what were the basic optimization questions? Like we know that there is some visual comfort optimization, but also there is selection of shape and form for the diffusing and redirecting the light. And also, I have some question. How did Mr. Akash decided to place these PVs? Like there was one line at the very bottom, one row, and also another row at the top of this facade. And yeah, like my questions regarding the optimization process.
So the question was the criteria.
Yeah.
What are the criteria for optimization?
Objectives of the optimization, actually.
Yeah, but Akash, I don't understand now. What are the physical parameters that you are optimizing then for? If you say glare, or if you say anything like that, what are the physical measures that you optimize? So is it looks, or is it, how do you measure that?
The angle of the shading.
The angle, or what exactly is this parameter that you're optimizing for? So maybe I try from here. Is better now? Yeah. Okay. So the question is, what are the physical measures that you optimize for? For example, what are you optimizing for? In looks, or how do you measure glare? How do you measure the deep light into your room? So is it, what is the parameter that you go look for? So it's standards. You're related to standard definitions and the Dutch standard NEN. And there it is defined how you visual define comfort. Okay. All right. Does this answer your question?
Yeah, actually, this is the metrics part. This is okay. I
Yeah.
get it, but what I didn't get, what did he optimize? The
Yeah.
angle of the shading. Of
So, okay, so now the question is,
left side
yeah.
of it, and like this was more geometry related
Yeah.
objective. What was
Yeah.
it?
So then the question, next question was, if we have now the criteria, what exactly did you change to optimize? What the angle or the color or what exactly? Okay, thank you. So we have to go on then. Thanks everybody for answering to the questions, and we will finish now the Q&A session because we have to go on and to keep a little bit up in the timing. So we will have now a new speaker from University of West England, Eleonora Nicoletti, and she's talking about photovoltaics potential for facade renovations. So Eleonora, we see you now on the screen. Yeah. Hello. Yes. Perfect. So thanks a lot, Eleonora, for the presentation. And I think, I don't know if you can be available for the Q&A. If not, we just have to go on without you in the Q&A. But nevertheless, thanks for being with us today. We have, as a next speaker, Pauline van Dongen in the meeting online. She is from Pauline van Dongen Innovations. So I believe this is a startup. And it's the presentation is called Scrolling Screen, a responsive building envelope for energetic renovations. So Pauline, could you please share your screen and then we can start.
Can you repeat the last one again? Maybe?
So Pauline, I don't know if you're online. Yes, maybe. Hi. So thanks for being with us today. We're a little behind the schedule. That's a little bit unfortunate, but we just can start with your presentation now. So you're talking about Scrolling Screen, a responsive building envelope for energetic renovations. And you're representing Pauline van Dongen Innovations BV. I think this could be a startup. And if you share your screen, we can just go ahead. Yeah, everything fine? Perfect. Yeah, all good.
OPV tapes, we're using
conductive material
to connect
the solar panels.
We're using
transparent monofilament jars to secure the solar films, which are actually woven into a float system.
And we're using
high tenacity yarns that give the material the required tensile strength.
All of
these materials have different properties in terms of flexibility, elasticity,
loads, which need to be considered throughout the weaving process. And the final yarn choices are listed here in this diagram, and the different mechanical properties related to them. So the main aim throughout this textile development process is that the high tenacity yarns, the rPET yarns, in fact, recycled polyester, must take the majority of the tensile load, and the float structures that hold the OPV in place must be protected from this tensile load. Our experimental tests have been carried out on different weaving looms, one of them being
a hand weaving loom, and the other one being the CCI sampling loom. Both have a weaving width of 50 centimeters. The hand loom has a shaft system of 4 shafts, and the CCI loom actually has a shaft system of 24 shafts, which allows for much more complex weaving patterns. So on these different looms, different specimens have been woven, which were extensively tested to investigate their structural and tensile behavior. I will give the floor to Stephanie to share more of our results.
Yes, thank you. So as mentioned by Pauline, the textile is challenged by the presence of both yarn and slur strips, therefore we need a design both very iterative, as mentioned. We had some material selection, we then study the textile development. We evaluate all the samples we have, and we review all the tests, and so we start again with material selection, etc. We started by a TPU yarn as a first sample with a plain weave and a double-sided float. We have tested those samples and decided to proceed on weaving them on a CPI machine. Those tested resulted because of the open mesh, but the strength was insufficient. Therefore, we decided to change the material, and we opted for rPET yarns. As a first sample, we had a hand woven sample with only rPET yarns, which we tested, and we decided then to weave in the CCI machine with monofilament for the float part of this textile where the are inserted. In the next slide, you see some of the specimens, the samples we have weaved, and the textile. Thank you. And also next. We have I will show you the results of sample 2, which we have tested according to, of course, the codes for uncoated textiles. We have reached a failure load of around 25 Newton per 5 centimeters, which is still with that sample B2 was still not sufficient. That is why we then decided to weave the same sample in the mechanically woven in the mechanical loom, because it produces a more cohesive weave, and we have tested those later. We have here you can see some of the results of warp specimens, and the force at break that is not yet at 3,000 Newton per 5 meters. We have also used digital image correlation to test the samples, which helped us evaluate the iteration between the solar strips and textile. And as you can see in the picture at the bottom, you see nowhere string in the strip, meaning that they do not undergo any test when tension, which was, of course, quite interesting to notice. Even though we know this from the tensile test of the fabric, we decided to test the solar strips um, to understand their functionality, the electrical functionality when pressed. And we have results that show electrical functionality until 500 Newton and 15 millimeters expansion. We have also tested the solar strips impact, the impact of the float design of the all the different designs we have chosen until now. And we have a peak performance that is reduced only by 10% with those what you see in the picture are monofilaments that cover a small part of the strip, and we were interested to know the functionality and the reduction of the energy. We have also done a design case study where we compared building. This one is Weststraven building in Utrecht, which is a building that has both glass and textile. We have applied our material context, the textile part of this building, and we have come up with 200 kilowatt system, which accounts for 4% of the building energy consumption per year, meaning one floor lighting is covered. And just to put this into a perspective, we know that by simply putting solar panels on the rooftop of this building, we would only have 160 kilowatts system, while if you place with our textile, the whole facade, you then have 100 kilowatt system. So that is just to show the potential of the textile we are developing. Yeah, I'll give back the presentation to Marie.
Yeah, so besides, of course, the quantitative benefits that at least preliminary we've outlined that Stephanie has just shared, there are also the qualitative benefits when it comes to the aesthetic experience and the material qualities that allows this textile to be used in places where otherwise energy would not be harvested. So in our case, with the woven material, we can play around with the opening of the textile in terms of different mesh structures, using different weave patterns, using different types of colors and patterning in the material. And by enabling these kind of aesthetic choices and design freedom, we also want to enable widespread adoption of solar technology into the living environment in a way that is also durable, also on an aesthetic level.
Very good. We have to speed up a little bit because I think we're a little bit over time now for your presentation.
Okay.
The last slide. So.
Yes. So we have now we have progressed within our research that has been developed after this paper. We have now reached the type 1 requirement we have chosen, and you can see some examples of the tests we have done on the images.
So this research, of course, is still ongoing, and we look forward to creating a material that is fulfilling all the functionalities besides the energy generation, also the qualities of waterproofness, fire retardancy, and UV stability. That is something that we're currently still working on. Yeah, we'd like to thank you for your attention.
Very good. Thank you very much for this interesting presentation. We will have you in the Q&A session after the next presentation, and then we can discuss questions. And just one remark to all of you. This paper is not in the proceedings book, but it's published in the Journal of Facade Design and Engineering. So the content of this presentation only that is then available through the journal. Just for the audience to know where to work. With some of the papers being in that journal, and some of them are in the proceedings, and just to remind you. All right, so now we come to the real life again, and we have as a next speaker Christoph Ermann from Innovation Production in Germany. And he's talking about the invisible solar panel, colored photovoltaic panels with high efficiency. Christoph, please.
Thank you. Thanks for having me here. Actually, how do I connect to the next file, to the next slide? Up there. Okay. Hopefully that works. So welcome to Aachen, the place where I live and where I study. So this is actually a home game for me, but still the first time that I present over here. And welcome to holy ground. For solar people, Aachen is holy ground for two reasons, basically. The first reason is the whole solar feed-in tariff has been promoted here and started here. So the whole solar boom was initiated actually in Aachen in 1991. And the second reason is the first solar facade with customized solar panels has been erected here. By the company I later worked for, this system I did not happen to make, but the second system I made. So today I'm going to present on photovoltaics. Innovation is a company located in Aschaffenburg in Frankfurt, so in the center of Germany. We do this since 10 years, and we do research now for 20 years. If you look into the photovoltaic world of today, you find products like this. They all very much look alike. They are hardly to distinguish. And this is exactly what we don't do. We do customized solar panels for building integration. So stuff like this, oversized, left-hand side, really not very many solar cells per square meter, very dense connection in the same panel for the bottom area of a floor-to-floor window, or stuff like this designed by the architects. And I'm pretty proud to say that nobody ever has achieved that we couldn't make his ideas come true, or her ideas come true. We were challenged a couple of times, and sometimes the prices we asked for were too high, so it has not been built in the end, but finally we made it in most times come true. What we do is we take two glass units and embed solar cells, crystalline solar cells, in between those panes by using a liquid gel, which enables us to have very much freedom. So size-wise, shape-wise, curvature-wise, anything is being given. And we are differentiating our products according to the color. We have 4-color series. The one is clear. There is only the solar cells can be colored. And on the right-hand side, top right-hand side, Ephone Color is the rear glass is being colored. Unichrome, which is what we're gonna focus on today, the invisible solar panel. The printing is in front of the solar cells. In decor, you can think of stone-like or marble-like structures if you wish. Now I'm doing this for 30 years. And in contrast with the text that is in the proceedings, I'd like to focus a little bit about more what can you do at all. And in the text in the conference proceedings, there is highlighted the invisible solar panel. So it started all with colored solar cells. And the bottom left solar cell is the standard solar cell, the black or dark bluish solar cell. And the solar engineers, the solar specialists can tell already by the shape and the color and the texture of those solar cells that this image is about 15 to 18 years old, because all the glittering solar cells on the right-hand column, they don't exist anymore. These are polycrystalline cells. They are not being manufactured anymore in the way that they were in that time. Now, basically, all of the solar cells are colored because on the last column, second row, this is the original color of a solar cell. The silver solar cell is the original color. So all the other ones, even the standard ones, can be considered colored. And we did projects like this. So this is actually a facade in southern Germany, silver solar cells. This is basically the non-colored solar cells, although everybody considered it being the colored solar cells. This is the most simple approach that you can do. You just take the solar cells as is and put them in the facade. Now, the question is actually, where, at which location of your setup can you modify color, knowing that photovoltaic is an optimized product. Core intention of photovoltaic is to generate electricity, to make it as cheap as possible to generate electricity. So anything that you do in front of the solar cell hinders the photovoltaic cell to operate because a lack of light is present. Everything that is as color in my eye is not as color in a solar cell, which makes it more expensive. Euro per watt peak thinking. So what can you do? So normally solar cells or solar panels are made up from a stack of material, typically glass interlayer, solar cell interlayer glass as shown here. And at every interface change you can do and modify the material. So you can, for example, change the reflection of the front surface, of the second surface, of the third surface, or of the solar cell itself, which was originally the colored solar cells. Or you can change the absorption of the material, the bulk material itself. From a highly transparent glass, you can go to a bluish glass, to a greenish glass, to a grayish glass. Or you can add absorption on the surface, which means printing of any kind. If you have, and you obviously need to remember anything that you do will reduce the power output, so increase the price by reducing the transparency. If you have a bifacial solar cell, a cell that works on both sides, also from the rear, you have all effects also from the rear side. In addition, there is not only one effect to be considered. There's a graph that I took from Macintosh and added some information for glass panels. There are lots of effects. There's a lot of different reflections on the solar cell because the solar cells are composed not only of one single material, but of coatings and metallization and bus bars and you name it. There's a couple of material involved and all of them have their specific properties that you need to consider. Now, the second step, what we did is actually two printings. This is a solar detail photograph of a solar panel that we made for a project in Moscow. And as you can see, there's two printings involved. The one is a bright whitish printing behind the solar cell that shows with the little dots around the solar cell to make the contrast of the solar cell from view from inside not as harsh, not a black and white pattern, but just a gradual change in transparency looking from behind. And we will see an image of the project from inside in a second. There's a second printing, a very translucent printing right in front of the solar cell, because the solar cell itself is dark, it's black. So there's a white printing in front of the solar cell just for the aesthetics. And this is actually a project, museum in Moscow. This is what you get when you do that. Still, it's a gradual, this contrast of cell and no cell area is still visible, but it's not as harsh and dark as it could be. So we did a lot of design work doing this. Now, when you try to do this, you need to find out how much energy do I lose and how do I do the same thing with color. If you do the same thing with color, just print a red, let's say red or blue, in front of a solar cell, you don't see the color at all. The reason is, in general printing, what you assume is a white sheet of paper behind the color. So the area that is not being printed in red appears white. In a solar panel, the area is not printed, is black. So the more paint you put on a solar panel, the more colorish it will be, the more, or in contrast to the white paper, the less you print, the brighter the color will be, because the color and the white add up. Whereas on a solar cell, the less color you print, the color and the black will add up, so the darker the color will be. So if I talk to people, or if I talk to printing people, could you help me with the presentation, please? Just quickly, and I continue talking. So the more you print, the brighter the color will be. If you try to print red, you need a white barrier in between. So this is what we try to investigate here. What we did is we took a solar cell, measured the solar cell itself on the point A, and what we do is actually we take single photons, single energy quantum, expose the solar cell with that, and count the electrons that comes from the solar cell. Each photon, each light quantum generates one electron. So by calculating the outcome, you can clearly see how many you lose. And this is spectrally different for long wavelengths, for short wavelengths. And what you see is a curve on the very top, the reddish curve. This is the original solar cell. And the more white you put in front of it, the lower the output will be. There's photons being absorbed and not being transferred to electricity. Now, this is true for white. You have a broadband absorption, so reduction in electricity, but this is also true for colors. You see the same thing. This is transparency curves for the printed CMY, and the K, the dark line is actually white printing. You see those transparencies for colors, and you need to combine both colors, the transparency and the white, because to see the color, you need the white in between to the solar cell to make it at all visible. So you see that the transparency goes down really fast. So the power losses by using absorption colors on solar cells is really heavy. So we did that for a while, but we don't do that. What we do, and now this is actually the topic of the talk and the paper, we do stuff like this. We use a non-absorption color. It uses the principle of interference. And I'm going to show you in a second what it is. And you don't see the solar cells at all anymore. What you do is actually you do a screen printing on the front glass that has small pigments. And each pigment is in the nanoscale and has interference. So it reflects on the top side and the bottom side and permits the one wavelength to go through and the other wavelengths to be reflected. So in this case, we wanted to have a red solar panel. So the red is being reflected and the green is being transmitted, and all the other colors are also being transmitted. So this is a ultra high efficient way to generate color without blocking the color for all the solar cells. Now I brought 2 glass units with me just to show. Hopefully don't slide down. No. Okay, so this is what we actually generate and what we get. And what you see, there is almost no color involved. The reason is these glass units are being exposed to light from both sides. And this principle works from both sides as well. So if you have illumination from both sides, the principle does not work. What you need is a dark side behind, and then you can see that the color will show up. You reduce the illumination from the rear, and then gradually the color shows up. Now this is still reflective, and this is reflective. So if you do the coupling, if you use the interlayer, then stuff like this appears. So this is actually the same glass. This is the green. No, this is actually the bluish glass. No, see, it's really hard. And this actually brings me to one of the problems. How do you quantify the quality? How do you check the quality that this green that you get here is this green that you actually want? Only by embedding, by direct contact, the color is being generated and visible. So it's really hard to tell the people, check if the color is okay, and the color is not visible. So what do you do? Or to develop new colors. How could I tell people, well, we need this new color, and they give me something and they tell me, well, this is the new color, and I say, well, I don't see a difference. So this is actually the same panel, the same glass. This is just in front of this, and you don't see any solar cells in behind because black of the solar cells matches with the black of the rear glass to generate a black surface, and you only see the reflection of the nanoparticles. We did the same thing that like we did before. We take the material. The black line, again, is the so-called EQE curve, the external quantum efficiency. We inject photons and calculate the numbers of electrons. And the blue and red and green curve show the transmittance. And actually, this shows the power loss, the direct power loss that you get when you have a purely green, purely red, or purely blue glass in front of the solar cell. At the bottom, with the green panel, you lose -7%, with the blue -10.2, with the red -12.2. This is in contrast to the former absorption printing technology, where actually you lost about 30, 40, 50, 60%, depending on the intensity that you desired. And the good thing about those pigments is that they are not on a flat surface, so there is no angle dependency. So the input angle, like an output angle, normally on coatings show a big variety in the aesthetical performance, because if you have a different angle to look at, the optical depth is different, and then the color changes. These pigments are randomly sorted in this coating. So if you take images from different angles under different illuminations, you can see the color appearance is quite alike. That's about it for the invisible solar panel. If you want to take a look, I'm going to share it around and I'm open for questions. Thank you.
Very interesting product. Thanks, Christoph, for the introduction. And we come to the Q&A session because we have the 3 presentations. I don't know to what extent Eleonora is still online because she had to go to leave for lectures. If she is not there, then I suppose that we start with the textile PV from Pauline. So are there questions in the audience to the textile photovoltaic elements? Maybe I start with one. Pauline, I would like to understand better. So basically they are knitted in, let's say, in the end, in the textiles as part of the textile. And so my question would be, if then for the circular use, let's say, later you can then cut them out and use for recycling, let's say, use them separately after when, because typically this textile have a lifetime of maybe 15 years or something. That's my experience from the big stadia at least. So when after 15 years you would cut them out and then bring them back. Is this correct?
Yeah, that's correct. In fact, the textile is being woven. So we're using a system of warp and weft, and the OPV material is at this moment in time integrated in the weft direction. And as we are using this float system that traps the solar panels, basically the solar technology is not glued in any way to the textile. It's integral to the textile, but it's not connected permanently to the textile. So that allows us to repair parts of the material in case needed. You can actually take out one individual solar panel and replace it. But also easily separate at the end of the life of this material, separate the technology from the textile parts and recycle these material streams individually. At the moment, the life expectancy of OPV material is 20 years. Of course, it depends on the degree of encapsulation that is chosen, as well as on the context of application, but that's for us at least a promising figure indeed in relation to the life cycle, average life cycle of textile architecture. Yeah, that's usually around 15 years, like you said.
Okay. And just another question, how about the cleaning? Do you need to clean these things? Because I can imagine that cleaning is not as easy as it is with a flat, regular panel, let's say. Or is this not a problem that you may need to get a certain efficiency?
What are you saying? I couldn't really.
Cleaning? The cleaning.
Oh, cleaning, yeah. Well, the cleaning and maintenance actually falls out of the scope of the research that's presented in the paper. It's one of the things that we haven't studied in detail yet. Of course, we want to develop a material that can be cleaned like any other architectural textile, and of course, considering the type of yarn and in what way dirt can become trapped in the cavities of the woven structure, especially when we're considering mesh weaves. That is something that we need to study more closely.
Okay. More questions from the audience? Not at the moment. But then maybe just stay tuned and we continue with the discussion with Christoph's presentation. Other questions? Christoph? Yeah.
Thank you. Always want to thank you for interesting that I understand you change from absolute colors to reflective colors. Is there also related to the efficiency of the solar panel?
The efficiency?
Yeah, I can imagine that with absolute that the heat of the students are efficiency for the panel. Is that does it play a role?
Just still morning? Yes, sir. Sorry. There's 2 points to that question. As I said, anything that you do in front of the solar cell reduces the efficiency of the overall panel, regardless if it's absorption color or reflection color, doesn't matter. But the reflective colors, or let's say put it like correct, the interference colors that permit at least part of it, have a much higher transparency on the one side. This is the first part. On the other side, the absorption, if you take a look at absorption, let's say if this is a dot of white, and this is outside and this is inside, if the thickness of the white is thick enough, it's still black from the inside because it's not transparent at all. So this completely blocks the light. So this effect is much higher than just the interference colors. First point. The second point is you raise the temperature. Anything that you do in front of a solar cell will reduce the heat. Solar cell, a colored solar cell per se is a little bit colder because at least a part of energy is in your eye, has been reflected and is not in the solar panel. So The good thing is the temperature will be a little lower. The bad thing is the transparency is lower, therefore the performance is lower. So, and by higher temperature, which is actually a really, really tiny effect, but the temperature gives you a little payback on the crystalline solar cell because there is a temperature dependency of crystalline solar cells with their power output versus temperature. As I said, really tiny effect, but the major effect is actually the transparency or the translucency of the interference colors versus the absorption colors.
I was having a question to that. What do you think from the development, to what extent can they be even more transparent in the future? Do you see this or is now?
It's a tricky question. Well, I do this now for 30 years, 31 years. And let's say 30 years and a half a year, people ask me, can I have different colors? I don't want a black solar cell, I want a other color. So we've been struggling in my entire engineering time to have other colors. Now, in the beginning, we had the colors. Well, they said, well, yeah, they're a color, but I don't like the colors. I want uniform colors. Okay, we thought about uniform colors, doing absorption colors. They said, well, sure, nice absorption and colors and uniform, but the power output is too low. So we developed together with glass industry and painting industry this interference colors. Now we have uniform colors and really high efficient solar cells, because at the same time the solar cells grew in efficiency enormously. 30 years ago, the solar cells had like 10%. Today we have 22, 23%. And if we use relative, or we lose relative 10% for color, 50%, we're still above 20%. So, and the physical limit is around 28%. So this is really, really a lot of development, a lot of work. And normally the additional price that you ask for stuff like that is not worth the energy gain that you get. One principal idea is to change the frequency of photons, but this is a completely different topic. There is ultraviolet light that normally we don't see and photovoltaic doesn't see, but there is pigments that transfer ultraviolet light to red light. And then you gain again like 2 or 3% relative. But this is another material, another process that you include. And we have a warranty of 25 plus years. So changes are not really easily made. So because soon sign the first contract, warranty time for this project is 25 years. This is a long time. This is a long time. So you hesitate to change anything.
Yeah.
It's like glass industry. They never ever change anything. They have to, I know. Now they have to.
So the last time we talked about these long and a couple of years, I'd say, and I always kept asking you about recycling, and that would be also my question now. What has changed in the recycling of PV cells?
Yeah.
What is realistic? I know the figures, but what do you see as a matter of practice?
Yeah. The original recycling idea was motivated by the price of the silicon. The price of silicon was so high, enormously high, that you had a lot of money to spend to do a process recycling it. Now the solar panel is cheaper than this window. So price-wise, there is no motivation for recycling. Although there is the green idea and stuff like that, with circular economy and stuff like that. There are projects going on, and I'm sorry to say that we are not part of the project. I would have liked to be, but we are not part of the project. It's a research project that will start in the next February. University of Cologne is going to participate, Fraunhofer, EASE is going to participate, and they will come up with an idea. Today, we have a very big advantage in our glass panels compared to the glass laminates that we saw in the beginning. These are hardly to be separated because the compound is so good that it's really tough to get it on. Our glass panel can be separated. So if there's a really special glass that we, let's say, made a mistake in the company. We can recycle that online. We just separate it, clean it, and reuse it. The silicon solar cells, they break normally, but the glass can be reused easily. And it's like quality like you. So for us, recycling is easy. We do it all the time. This is why we don't, why you're not part of that research project. We don't need the research actually, although I'd be interested to participate. But for the standard panels, which are the majority, like 99% are the panels that we saw in the first slide, there's hardly any recycling. And just because of the price, it's not worth doing it. They just shred it and put it as infill, as foundations for streets or stuff like that.
But I think then the other question would be, are there any critical elements in this setup? Because I think there will be a big discussion will be on the sourcing of the materials. And once the sourcing of the materials gets to a critical point, then suddenly all the simpler things come into play again. It's the same like now with the energy prices. So I think thinking ahead a little bit, which elements are in there that are critical that you would say need either another type of material to replace or need to be recycled in the future?
Yeah. That's again not a really easy answer to answer question, so I'll try to make it short. The amount makes the poison. Salt per se is not a poison. Sugar per se is not a poison. If you only eat salt, you die. If you only eat sugar, you die. So the amount of material being used is the reason. So all the materials that are in photovoltaic panels are not per se poisoning. They're not cadmium, they're not tellure, there is no excessive lead involved. So all the really harmful, like radioactive material, none of this is in there. But still, it's material to be reused. There's silicon, there's copper, there's tin, there is a little lead for the soldering. So in the future, there will be restrictions on which material can be thrown away, but the majority weight is glass. You have like 3 millimeter glass and 0.5 millimeters of interlayer in solar cell. So just from the material, 60% of the stuff is glass. This is quality like glass like this. Nobody cares about throwing this away or recycling it. Okay. So the majority is okay. Material-wise, it's a very tiny fraction. And this is not an issue of today, but it will be in the upcoming years for sure. Like everything, like sugar and salt.
So I think this is it for the morning session. Thanks for your attention. Thanks to all the speakers for being with us. We're going to reassemble at 1:30. Yeah, and we have now 45 minutes as a lunch break, and then we will come back. We will have 2 parallel sessions again, and looking forward to continuing.
I didn't hear anything. Should we start? Can we continue?
No, just 1 second, please. We're trying to bring back.
Okay.
Yeah.
Great.
Welcome back. We start now with the environment session, and our first speaker is Christian Schmidt from the German University in Cairo, and he will talk about earth products, and the title of his talk is Digital Imperfection, from Digital Imperfection to Circular.
Okay, then I start. I hope you hear me better. I had some difficulties to understand. So today here, welcome from Cairo. Thanks for the invitation. It's me, Christian Schmidt, and Federico Garrido, today from Karlsruhe, and Rodrigo Brun is not able to join, so it's only the two of us. As introduced, we are tackling Earth. And Earth, as you know, I heard it just the last talk in the other room was also about Earth. But here in this room, nobody talked yet about it as a power skin or a power material. So basically, Earth is available nearly everywhere in the world. As you can see on the map, and also the black dots also mean that it's worth being looked at, and not only a building material. And as you maybe already know, we already have some kind of good milestones in the last decade. So Earth went back into focus of architecture, and also some really interesting milestones have been developed. Only here, these kind of two milestones, Ricola building in Switzerland, and in Austria, of course, the well-known house Rauch by Martin Rauch and by Roger Bolshauser. But not only in architecture, also nowadays again, or especially at universities, it got attention. And this is why I also was affected by Earth again when we taught this with Martin Rauch and Anna Heringer at the ETH. And we also went back to, not back, we went with the students to Africa, to Tanzania, to build a house, or several houses, in a funny way, in those areas where material is still there and could be used. Also, the tradition is changing away from the material, and we some kind of want to bring it back. So, of course, it's easy to influence students to go back to Earth, but it's quite complicated also to affect the people who are living in these areas for the interesting parts about this kind of material. And when we, for example, then go also in the industry, you see here, this is, for example, another research project with Rob Technologies and Rematter Earth, where they find a new way of building with Earth. Here it's a ceiling and a slab for a building in Switzerland. So I'm really happy that the material is back into the focus. But this is in Europe, and in a funny way, Europe is seeing this as a very interesting material. But in other countries, like also not so long ago in Europe, Germany, Switzerland, wherever, the building was, the material was not very interesting. So I'm quite happy, or I'm not quite happy, it's quite a challenge also to make the material interesting again in other countries, where the tradition for using Earth is actually much higher. So, for example, at the GOC, we tried, Federico and me tried to make the material more interesting again. And like it is actually also in Switzerland, it's not so problematic to get students or architectural students, especially, into touch with the material. It's then the thing, how do you get everybody in touch with the material? Because the material is still addressed as a material for the poor. Even if there's a nice tradition with Hassan Fatih in this kind of buildings, and they're all well known. But first, we need to get also with the students into the material, and the students in this kind of case are more or less also a representative for the population where we would like to build with. So what we want to do is, of course, we want to get rid of the idea that the material earth is an old-fashioned material. So what we did, basically in the studio, Unplugged Matter, Earth the Materials, we tried to get in touch with the material again. In a playful way, we tried to, and we did also, we tackled the idea about the bricks, analyzed what a brick would be, and how, this is then the tricky point, how we can use the brick, or how would the brick look like, and how would we then use the brick or the result to get this kind of brick in an interesting idea, or basically also an interesting form, to get into a playfulness, to make the material more interesting again. So at this point, my colleague would take over, Federico.
I don't know if you explained this already, but this workshop was the combination of two separate elective seminars, one dealing with earth as a material, and the other one, which I led, was called Robotics in Architecture, was teaching basically robotic fabrication and parametric design in a broad sense. So we came to the idea to design a sort of parametric wall with the students, and then to design a workflow that will allow essentially the design and the manufacturing of the wall in one single process. And for that we used HoloLens, which is a mixed reality device. We can explain later what it is, but essentially the workflow of this research was, first, once we have the design of a wall, we would have let's say a stack of bricks, or the position of the bricks in a stack where they were stored, and through a parametric definition we could stream the final position of each brick to the HoloLens, and the HoloLens would be used by a student, and then he would get the instructions of where to put that brick. So what we essentially wanted to do was to create a workflow that allowed the students to build a brick wall without any documentation or without any measuring device other than the HoloLens. Next, please. So this is more or less a diagram of what actually happened, and this has to do also with the imperfection character of the bricks, because of the students made this bricks. This was the Corona semester, so the bricks were not really super precise, and then we need to divide them in two separate stacks, and that's we could let's say create this parametric definition and procedure in a way that the program would tell the student where to pick up each brick. If it was a large brick or a medium-sized brick, then the system will tell the students where to pick it up, and then of course where to put it. Next, please. So this was essentially the procedure. Also, I mean, the idea behind this on my side was that Originally, we wanted to use robots for this task, but because we have some issues with the university and again Corona, we couldn't. So we decided to use the students as robots. Next, please. This is essentially what one would see from the outside. That's Professor Schmidt there with the HoloLens on. From the outside, we cannot see anything, of course, because the HoloLens, for those who doesn't know what it is, it's called a mixed reality device. It projects in the user, in this visor, it projects a 3D model, for example, or 2D graphics, and then you can see, let's say, the reality, and on top of that, one can see a 3D model in real time. And next, this is what the user would see. We also use these QR codes for location. So the next one, please. So let's say the bricklayer gets a real-time position of the virtual brick wall and the real brick wall. I think this is a video. Can you press play or?
No, it's not a video.
Okay. Then this is essentially what the user receives. It should be perfect because of the camera of the HoloLens doesn't match the eyes, but the user would see everything as a perfect, let's say, superposition between the imperfect brick wall and the ideal virtual wall, and also where these bricks should come from. Next, please. That's what essentially my students provided. This is procedure in which the definition could pick where this brick should come from according to the height of the wall at a certain stage, and also we can show that later. We needed to update those values according to the errors in the bricks and in the mortar. Next one. Yes, this is what the procedure looked like. We have at all times, of course, control of what everybody saw. Was it related to the ideal wall that the students have designed? And again, every 3 or 4 lines, we need to take height measures just to adjust our virtual model to what was really in there.
Yeah, and this is what we basically see through the lens, and in the end, of course, maybe the precision or the logical idea that was already elaborated several times was to use the robot, but also during the process and during using the material, we realized that actually this kind of idea using the bit of less precise HoloLens would help us also to get more, again, the human people in the focus of the process. And in the end, especially with this material, it made much more sense that we did not use the robot at all, but instead used the HoloLens and basically the augmented reality to give it back to the people. And currently we are still working on the idea of even reducing or getting rid of the HoloLens and just using augmented phone. But we are not yet that far, and it's getting losing, of course, also some kind of precision with this kind of idea. So these are also other impressions, and you see the gloves we did not use actually because we used earth. It was this kind of confusion that everything around Corona is problematic, and it's not good for the cameras because it's also the idea of getting also in touch with the earth, getting dirty. Unfortunately, then we choose for gloves. So you see the wall is growing. You see, even it's just a university, it's not yet getting in touch with the people, but we caught the attention, at least from nearly everybody at university during the workshop, And for us also the idea of bringing people together and having nearly more, not a very technical construction, it's more social construction. To be honest, also we are not intending of building a complete house with that, but the idea could be, of course, that we get people in contact with the material for their own project, and to make the material by integrating the people in a much more interesting way. So in the end, as Federico mentioned in the beginning, it was a cooperation between Unplugged Matter, my course in robotics and architecture, and also the video documentary was also quite necessary, because we realized also by documenting it actually that we have this kind of social component, and we would like to explore this even more. So it was a fruitful cooperation from different competences with material, responsive design, and the robotics. And for us, or for me, that I'm coming already from the earth material, the cooperation makes then the material much more interesting. And I think this kind of dialogue is also necessary. I don't know how much time we will have. We can have a closer look through the movie, because it catches actually the moments that we had there very good.
It's almost up, or this is up, depending on how long it's.
Perfect. We also wanted to reflect about the building process, and we also had the ambition to place a human being again in the center of it. Even if it's a virtual process, we want to have a human being.
So in the end, we underlined that Earth is much more than a vernacular material, and we involved the digital to produce again a contemporary and elegant idea about architecture. And what is for us necessary to emphasize the collective experience of building with sustainable materials, and then just using technology to create a shared understanding of a building with the community's hands, and by this to find the post-vernacular new narrative for the material that we used. And last but not least, that's also part of the title, and this is of course for the material itself, but maybe also for processes in architecture, in education, that we can reuse the material in the next semester and do another sculpture with another ambition out of that. Because we know all that in architectural production, we throw away a lot of things. And with this, we are already at the end. Thank you too.
Please stay around for Q&A. We'll have that, and we have two talks. And I would like to welcome the person who is from it's almost. It's fine, yeah. Okay, and we're going to talk about establishing benchmarks for low carbon circular plastic design on refurbishment projects. So yeah, thank you for having me here. So my name is Melissa. As already mentioned, that I'm gonna present today. It is the recent research work that we did within the team together with my colleague here, Christina Kokeli and Laura Kraft. So the topic is about establishing benchmark for low carbon circular facade design, specifically on refurbishment project. Should I?
Yeah.
Yeah. So yeah, our work basically stemmed on a decarbonization project that we did in the EU. With the target of knowing what we did a couple of facade intervention where we want to assess the carbon emission and the circular impact of each intervention. So if you look at the built environment at industrial level, we have to kind of see or like look at the key drivers that we have, and definitely we evaluate our industry, also how our industry works and what does our industry do, like impacting the environment. So based on the EU Commission, 50% of all extracted we are responsible for 50% of the extracted raw materials. And also they are responsible for 35% of all waste generation. 36% of all the CO2 emission also comes from the operational building energy, and also further 12% comes from the associated embodied carbon of the material that is used in the building. So what does it mean for the built environment industry? As a response to the climate emergency, the EU has established a couple of or multiple policies where it sets or like to ensure that we will manage to kind of reach the target of carbon zero net carbon by 2050 with an interim of 55% carbon emission by 2030. There are a couple of policies here that you can see, but the one that is more relevant, the most relevant for our work is the Innovation Wave Plan. And it is also has the highest potential, I would say, in our industry, because they recognize, or the target is actually to double the renovation rate by 5 million buildings in the EU will undergo renovation in the next 10 years. That say that this building also require higher energy and more efficient resources. In order to comply with the current EU taxonomy, there are also a couple of key drivers here. But one thing that we look at here specifically on kind of including the life cycle carbon assessment on projects. In looking at the theme and topic of circularity, we kind of start looking at how the circular economy model works. So for those who's not familiar, so it's kind of essentially the regenerative economic model, which is stimulated by the biological and technical resources. So it is a really fundamental transition for our industry to move away from the take, make, use, and dispose model. There are a lot of bodies at the moment, including the Ellen MacArthur Foundation, who's advocating how our industry can actually move towards the more circular model. This is one diagram that they produce, biological cycle of it, and for us the most relevant is the right part where it's the technical cycle. In looking at the EU, the color slightly changed, but right. In looking at the EU waste hierarchy, our main focus now is to kind of look at the high value of the waste hierarchy and only scaling down to recycle when all the other strategies have been explored. Give you an example of one project we have recently in London. It's 1 Brighton Square. It's a really good example of renovation project, and it just also received an award at the Society of Facade Engineers, where we actually saved 40,000 tons of carbon. The second one that I want to show is also one of the great examples of renovation project, also received the same award as the previous one. And here we actually saved or reused over 7.5 kilometer aluminum glazing bars from the old buildings. And also we saved kind of like, we take 16 tons old glass and remanufacture it to be a new architectural glass. So how can the principle of circular economy be incorporated into facade design? This diagram is a modification from the previous one that we have seen. What is more relevant for us is the technical cycle, and it can be identified for facade component, system, and materials. And the idea is to keep them within the loop, so as long as possible. This one also the modification from the EU waste hierarchy, but more into the facade context or building envelope context, which provide a useful guidance for us as a tool for design decision to kind of transition our industry towards the more circular design. In terms of strategy for facade design, what we want to do is absolutely look at the very top part, the very first part of the diagram,
which essentially refusing, rethink, and reduce the non-functioning facade component, also include the overperforming facade system. And then the second one is more that we prolong these components for as long as possible. So in the past, or currently still, that the facade sustainability has been defined to heat gain, heat loss, natural ventilation impact on our operational energy performance. But in order to be really use the closed loop approach, we have to kind of look a bit more to the bigger picture and then actually see what happens to those materials before it's been used in the buildings, and also what happened to them afterwards. So there are a couple of strategies and tools that you can use. It's an open source that you can use for methodology for circular assessment. We recently published our guidance or toolkit for client to explore strategies and action for a more circular construction. We are also involved in the CWCT body to set out strategies specifically for building control. Here is going to the test case that we did for our specific research. We used a hybrid method where we assess the life cycle of each material and component. So we used both the life cycle assessment, also including the building energy simulation for stage B, which we are focusing on stage A1 to A5, the building when it's being replaced, so the stage before, and also the end of life of it. So our LCA work was done on the desktop spreadsheet that we developed within the company, and also it has been kind of adopting the current CWCT methodology. And for you who's not familiar, we are using all the information mainly from the database that is available, and also EPD from the manufacturer. So essentially, the EPD is an environmental product declaration, which kind of shows the environmental impact of each material in the product. Here, what I want to explain is just there are a couple of boundary conditions that we use for our test case, and the 50 years, so the estimated service life, we take 50 years for the primary components, that includes aluminum, so framing, and also insulation. And for the secondary components, it includes the glass, gasket, and sealant. For our test case, this is based on our current recent project in Brussels, Belgium. I cannot say the name of the project due to confidentiality, but to explain you a bit more of the project is that we have a high-rise building where they have a unitized curtain wall system, and we have the low-rise part of the complex, we use the stick system. And it's kind of interesting because their module and configuration of both unitized and stick system are kind of the same. So we kind of compare them at the end, what's the difference. And here, the building has almost reached 20 years old. So we know that essentially in the next 5 years, most of the secondary component will reach the end of life and some intervention needs to be done. We did a calculation, or like we exercised 8 different scenarios, which essentially the first one is the minor intervention, where we kind of have an aim to improve the curtain wall performance. And we have the major intervention here, the upgrade system, which essentially the same target, same aim to improve the current curtain wall performance, but also we have introduced the more circular approach. For this specific presentation, I'm going to focus only on the 4 different scenarios here, essentially the upgrade system as major intervention, where scenario D, where we try to use as much component as possible, and scenario E, where we introduce bioregenerative material, in this case it's timber, and scenario F, where we introduce a new material but with high recycled content. And as a comparison, we use scenario D is as kind of the worst case scenario, which is the business as usual, where we didn't consider at all circular approach or a more low carbon design. This is the result of our scenario D, which we try to reuse as much of existing component as possible. In this case, we try to reuse the aluminum sunshade and framing system. And you can see that slightly strange with the color diagram, but okay, I don't know what happened, but it's not supposed to be with this color. So we can see that essentially the highest value of the life cycle carbon is still so you see like it's supposed to be basically blue. It's the triple glazing unit, and the bottom result shows that there's this material waste of existing buildings. So essentially, it's what we are trying to assess what happened to the existing material before it's being refurbished. So how much percentage material goes to the landfill or recovered or reused or recycled. And the other diagram is to assess what kind of new material comes to the building before being refurbished. The next one is scenario E, which we try to introduce hybrid timber framing, just to have it in the mind behind. Like when we did this calculation, there is still a good proportion amount of aluminum framing in the hybrid timber framing in the unitized system. So essentially, this also contributes a lot to the total embodied carbon, because in order to achieve the same structural properties for a hybrid timber framing, we still have this good amount of aluminum profile in it. The next one is the system where we try to introduce recycled content material in our exercise here. We try to introduce a 75% aluminum framing. Also, we use the current or like the newest glazing product in the market, which contains 70% recycled content, which essentially this new glass product will have an impact of 40% less embodied carbon. This is the worst scenario where we use all virgin resources, and also all the material before refurbished will just be sent to landfill. Again, sorry for the color coding because it's supposed to be with the label there, but okay. I'm gonna explain like the blue part is actually the stage A to 4, A to 3. And the yellow one is supposed to be the stage A4 to 5, and the upper part, the gray one, is supposed to be B4 and C. Sorry. Talking about a little bit about this result, we can see that scenario F, where we introduce high recycled material content, it has slightly less impact on the embodied carbon compared to scenario D, where we try to reuse as much as existing components. And also that you can see the scenario E still have kind of a higher embodied carbon impact towards the other two scenarios. What we have to pay attention here is perhaps that in order to see what kind of comparison we have, we also have to kind of look at the bigger picture, that scenario D, in our opinion, when we did the research, is still the most favorable one, because we try to kind of reuse as much as component as possible, which means that we send less material to the landfill. And if you go back to the like couple of slides before, that the reuse itself, the reuse strategy still stays in the upper waste hierarchy compared to the scenario F, where we recycle the material. So this is something that we need to kind of rethink when we do the assessment, try to think about the indicator of more circular approach. Here is a short summary of the operational carbon, where we can see that the upgrade system, so for the three scenarios, D, E, and F, we're able to save 12% of the operational carbon. And obviously also it's impacted by the fact that in this scenario, we try to reduce the window to wall ratio to 50% compared to the current building. This is one of the strategy that it's not our main focus in this exercise, due to the fact that it has quite significant impact visually, and it adds complexity for refurbishing projects. So essentially what we want to test is like if we don't use traditional opaque glazing panel, but instead another type of opaque material as raised cladding. However, we see that the scenario G has quite a lot of potential if it applies to the new building. So you can see all the comparison of other alternative material to an aluminum, say for raised cladding or opaque, traditional opaque glaze panel. Here is the overview of all the calculation that we did. As I mentioned before, the alternative material has quite interesting value compared to normal opaque spandrel glazing or aluminum PowerSKIN system. But also here we can see that, again, the discussion before, that the scenario D, where we try to reuse as much component and existing components as possible, is still the most favorable one, because it has the least impact on waste, and also it has the least impact or low impact in embodied carbon. This is the result or the summary for the unitized curtain wall system. We also did the calculation for the six curtain wall system. I will not explain in detail, but you can see here the yellow color on the chart, which is supposed to be the A4 and A5. It is slightly higher than when we have a unitized curtain wall. So one has to kind of rethink that the factory assembled or on-site assembled, whether we produce more waste on-site or in the factory, this has a lot of impact also on the total embodied carbon. As a conclusion, there are a couple of points that we want to reflect. So the first one is that we think it is really crucial to set up a measure during the refurbishment project, and also to set a timeline when actually, so to kind of understand and evaluate when actually we need to do intervention and in which sense. It also means that our higher priority is to kind of prolong the facade life as long as possible before doing any intervention at all, or before doing major intervention. Second point is that we kind of summarize that reusing existing component has the least impact on waste and still resulting in low carbon intervention, which is in line with the waste hierarchy that we mentioned before. The third point is that we shall work more and more with industry to maximize the quality and potential of facade components. So in order to have this component or system and material to be able to be reused, refurbished, or recycled. So essentially, it is to set a strategy and methodology with the industry together to remove how to kind of remove and dismantle each component without it being broken. The last point, which is probably interesting for some architects here, that obviously circular approach may impact our current architectural intent. So what opportunity we have I hope for the near future, that one of the approach to low carbon design is generally to reduce the weight of the facade. So this again come back to the strategy that I mentioned earlier, that we have to kind of refuse, rethink, or reduce the non-functioning or overperforming facade system or component. And it also means that a more relaxed specification requirement to reduce the amount of energy and waste without compromising with the safety and performance, but still it provides resilience. So this opens a lot of discussion within the industry and expertise, that perhaps one has to rethink if our current specification is unnecessary overperforming. So this also has something to do with the discussion whether, say, triple glazing unit is more sustainable to double glazing unit. We can discuss it later. Perhaps I don't have enough time now. The next point is to have always a collaboration with the design team to kind of move up to the waste hierarchy. So kind of before doing anything, you try to reduce and refuse. The last point is to work more with industry to establish best practice benchmark for higher recycled content materials. So that's it from me. Thank you very much.
Thank you for the slide. Going to the Q&A. We do that later? Yes.
You did later.
Yes. And we're now moving on again. Next.
Yes, thank you.
Very nice. And talk about multi-species in random.
I can't hear very well, but
I just read out your title.
I hope you can hear me good.
Should I share my screen yet? First. Can you see it?
Can hear you. But we now see your screen in present mode.
Okay, perfect. Then I'm gonna start. My screen and hear me well. I'm going to talk today about how digital design tools and additive manufacturing will potentially contribute to the improvement of biodiversity and microclimate in the city environment through the creation of the new building environment. My name is Julia Larikma, researcher at the Professor of the Digital Fabrication at the Technical University of Germany. This research was conducted together with my colleague Hilda Professor Dr. Catherine Jortler, together with my colleagues from the Chair of Building Technology and Climate Response Design, Dr. Arjun Chokran, Professor Thomas Auer, and together with my colleague from the Chair of Terrestrial Ecology, Professor Wolfgang Klein. So urbanization is one of the main contributors to the climate change. Causes urban island spread and biodiversity loss, which leads to the domination of several species in cities. They can adjust to harsh human-made conditions, such as, for example, pigeons or rats, while another species in the need of protection are extinct. Another problem we are facing today is many existing buildings with insufficient ecological quality. We see this need of renovation as an opportunity to create new climate performance envelopes for this building and include hosting elements for animals into these envelopes. Future vision, a well-planned coexistence of humans and animals will be possible through this envelopment. Also, it will contribute to the improvement of biodiversity as one of the key factors of mitigation of climate change. In this research, we present an additional findings of an integrated design approach that merges expertise from terrestrial ecology, digital technologies and digital fabrication in architecture, and climate response design. With the help of the computational design tool and digital fabrication, namely additive manufacturing with clay, we try to develop design studies based on certain parameters like the species and human needs in order to create inhabitable and climate performance building envelopes. We selected research to design methods with our studies. For us, it was important to integrate digital technologies on all stages of the project and integrate interdisciplinary collaboration on all stages of the project. On the left side, you can see a building example in Germany with integration of wet and dirt nets into conventional concrete building structures. Whereas on the right side, you can see this fabricated rectangular old net. Research to try to combine the advantages of digital fabrication to integrate them into safe elements that will become multifunctional in comparison to the traditional building technique. To assist our research with design method, we developed a case study on the example of the Johnsburg building in Munich. This building is located in the area strongly affected by the urban heat island. It also has greenery in front of the facade, which was crucial for nurturing the potential species. This building has enough free from windows walls for placing nets. Also, social factor was important. It's dormitories or student facilities where people reside temporarily, which makes the building perfect for the experimental project. In a preliminary stage of our design development, we find two groups of design criteria. First group is performance-driving criteria such as species and human needs and microclimate performance. Is realization criteria such as construction and additive manufacturing with clay. Performance-driving criteria include species needs such as geometrical parameters of net and human needs such as design quality, whereas microclimate improvement, a reduction of urban heat balance effects due to both to the species and human well-being. We With structural ecologists, we selected 3 species for this specific urban context. They are house, sparrow, black-red start, and common with Australia. We define certain criteria that we can influence with the help of our design. For example, height of the nest on the ground, number of the nests that could be placed near to each other, the preferred temperature for the species, and also information, for example, the regularity of cleaning of the nest. The geometry parameters such as size and shapes of nests and nest entrances could also be, of course, influenced by the set element geometry. Microclimate parameters, namely the reduction of solar days and reduction of pressure, was also a base for our further design development. To our design development and microclimate performance specifically conducted first the analysis of the current state of solar days in our building. We took the west, in our case, and based our analysis on energy flux weather map for Munich for the hottest period of the year, and we conducted analysis with the help of Ladybug for years. A similar analysis we conducted for the wind pressure for the annual analysis period for the 2 strongest streets in these urban conditions, north and west, with the help of edit 3D printing. Moving to realization criteria, we've chosen ventilated facade system as a high efficiency in terms of insulation properties. However, for us, it was also important that this system has a flexible size air layer, which actually could be a space for PowerSKIN and nest behind the facade surface. The disinfection with clay had some boundary conditions which were important for us, such as the material properties itself, the fact that the element should be stable during printing and drying, and the fact that the 3D printing occurs in layers, so geometry needed to be interpreted in layers. The usage of the ventilated system was also the idea of retrofitting design approach. We wanted to mix standard flat tiles that could be either industrially or additively manufactured fabricated with climate performative additively manufactured tiles, with climate performative additively manufactured tiles with nets. All the tiles have the same. In order to reduce solar radiation through subshading effect and wind facade pressure with help of vertical geometry, we deformed the front surface of climate performance tile outward. By controlling 3 points parametrically, we created different depths and angles of this hole, 10 centimeters. 3 parametrically controlled points on the bottom of the tile can help us to vary the size and shape of the entrance opening from species to species, providing them the access to the nest. Each tile has the structural profile on the backside in order to be mounted into the standard substrate. Nests are located on the back side of the tile. They are also located within the air layer and insulation layer without interfering the parent wall structure, which makes this approach especially relevant for renovation purposes. Also, the tiles with nets permanently closed tops and chemically closed bottoms, so birds and litter from birds cannot interfere with the inner system. An important feature that tiles could be mounted out after assembly, so regular cleaning could be provided for the nest. Moving to the bigger scale, we based our distribution of this facade element on the facade with the most performative clay. We based it on 3 factors. First is the amount of solar radiation, second is wind facade pressure, and third factor is the species distribution on the facade. On the right side, you can see these 3 maps merged into one map. The line horizons corresponds with the higher amount of solar radiation and wind facade pressure, Therefore, climate performative tiles distributed there. And darker zones should be covered with flat tiles, whereas smoothness distributed according to the species preference. This map was the base for parametrical distribution, which resulted in different pattern design options. Once this option was chosen, then revised manually and be adjusted to the urban context and transferred into final supply. In order to verify our assumption that the radiation could produce shade and effects, we conducted the simulations of the facade fragment, the fragment of the facade area. And we found out that with the help of this cascading folded tiles, the fluoridation could be reduced up to 90%. In order to verify the fabricability of our idea, we input a set of 9 ceramic tiles and assembled them into one-to-one scale project. Here you can see the process of the 3D printing of one ceramic tile to performative tile. The initial geometry of the tile was represented by surface-based geometry, so we needed to slice it and convert this slice into 3D printing parts. The initial size, the target size of the tiles was around 11% smaller because for the 3D printing we calculated potential shrinkage from drying and firing process. Here you can see the process of printing of the tile with the mat. So small human assistance was needed to abstract in order to print the mat in one pass with the whole tile. And it took around 70 minutes to print one tile. The 3D printing process was followed up by dry process. The dry process occurred in the same laboratory printing with a humidity level around 50%, which resulted in very quick and rapid and heterogeneous drying process, which unfortunately caused deviations in shape, especially twisting, in comparison to the initial shape, up to 15%. So it was our biggest obstacle. After tiles were dried, we fired first the system fire at a temperature of 900 degrees, and second, we glazed them, fired again at the temperature 1200 degrees in industrial oven. No additional deformations or cracks occurred during firing process. So integrated design approach for enabling wildlife inclusive site renovation has shown that the integration of design tools project takes and help to link inputs from several disciplines within one computational model. It also helps us to do design more multifunctional on all levels, from the facade element to the overall facade design. More parameters regarding species behavior are needed to develop this approach. We also successfully fabricated one-to-one prototypes with these deformations. However, of course, these obstacles needed to be overcome. However, additive manufacturing with clay has shown that great potential for site-specific solutions. Moreover, it can contribute to make design of elements for animal groups multifunctional with comparison with traditional building things such as concrete buildings. And speaking about future work, we can divide it into three directions of steps. First, of course, improve a fabrication process to overcome major obstacles in drying. Maybe to do simulation for longer and to recalculate these deformations, or to try another fabrication method, such as printing of mold. Second direction is, of course, on the side of terrestrial ecology and climate performance. On-site tests would be crucial for us to document species behavior, test the durability of the prototype, to test of the prototype from the species and from the humans as well, and also to document to verify climate performance on site. The second step will, of course, contribute to the development of digital design tools and make this digital design tool better. We would also like to thank our industrial supporters at Melting GmbH and Linkinger Bade GmbH that made the prototype possible. And that's all for me for today. I'm happy to discuss it.
Thank you. We now have Q&A session, and we start with are there any? I have one. So your angle is modern working with products. Can you hear me? You look like you don't.
It's very difficult to hear you, to be honest.
Okay, I'm trying to. I'm putting the mic real close. You change the mic.
Jetzt ist besser. Sorry. It's now better.
Thank you. Approach is to modernize working with by as a how will it is that potential?
Actually, nothing of this is exactly like you mentioned. In the end, we tried to make the material interesting again because we lost the interest. Especially in Egypt, also because of Hassan Fatih with the book, with his book about the material for the poor. And I want to get rid of the idea with students and with the digital tools that it's a poor material. And in the end, you store bricks are, at least the first one, the happy little Corona bricks. They are not emphasized because they are from Earth, but basically, we make a story about that. And the story should make the material more interesting. We did not really modernize the way of building bricks. We did not modernize to make a new wall. I mean, Kamal made this kind of exercise years ago. We try to do this kind of tools for normal people without robots, without special equipment. We make it everyday use because it's an everyday material. Well, the second wall looks much better, and not necessarily the wall has to be curvy or formy or whatever. We tried also the idea in the second part of making a self-tunnel effect, which works also quite good. At least it gives it a reason. I cannot yet say if the material is getting attention because we did not build a building, build a university project, but I can tell you that I can get a lot of attention from my students about the material that was used to be old-fashioned, and that's already all I wanted.
Thank you. Okay, thank you, Christian. Very interesting how you work in Cairo. Thank you for that. In this
Again to me.
Yeah, just if like works because obviously we have technical.
Yeah, it's very difficult to understand.
Okay. Better like this?
Yeah, better.
Okay. My question to the second presentation. Operational costs during the operation building typically have a very big impact on life cycle. So I think this is also incorporated life cycle.
And the question again is still to me. No.
No. Sorry. Let's do the second
But
presentation.
you can hear me. So the question was about cost. Or
Operational.
so in specific in ours, it was a research project essentially, but in this one, the operational cost we didn't include. We didn't compare cost.
Operations of alpha. Lifetime. Much larger.
It is much larger, but actually, after I put it in the intervention. And if we go to the value, but we have to be a bit careful because the worst case scenario is ratios is also require more ratio. In our intervention, we also not only to audit carbon of the facade, but also we want to find what's change the window ratio.
Talk a little bit so I know other things. Your presentation, well, you just mentioned we're looking at offsetting, improving the physical performance as well as lowering the embodied. You had an option for busy or analysis results that uplift in embodied carbon offset at operational carbon. No, like when was the payback? Years.
For this specific research, we did not take that into consideration because the triple glazing is from the fibers essentially, like to reach the fire U value. There are a bunch of studies there also from city now that our colleagues part of the body of where we actually kind of do the exercise and what payback time. For instance, in another discussion about the balance between what is part. So it's one thing that I didn't mention at the end, but it's more like have an internal. But you know, like considering that in the future when we were trying to reach net by 2050, so maybe hopefully we have a cleaner, more sustainable energy resource. So thinking about like whether double glazing is possible in the not with double glazing, but you require a little bit more heating. But then, you know, since we have a cleaner renewable resource, perhaps compromising.
Yeah, we'll have a lot of questions on how to measure circularity. So, you have a really qualitative talk. I noticed in your presentation you take it back in terms of emissions. Is there any other metric that you have developed in your office to measure suitability of usable components and because We also are trying to make sure category is such an open topic that
So what we try to do is first, it is a really qualitative measure. Then we try also like internally like how to measure this more quantitative measurement. So what we try to assess from the beginning is like to put the fiber of a lot. So these key indicators that have the carbon, also the waste, which is aspect of also the material resource. So the whole material resources in the end of life. So in our calculation for the 50 years, already considering that within 25 years, then have to. Of course, there are also a lot of design mechanisms that we assembly and all. Probably also know about it. So it's something like a really ongoing topic at the moment, and I think that we have more interaction with the industry with a lot.
Maybe another question that doesn't work. I think there's 4 dimensions. We have energy dimension, and we have to make recycling of energy zero. We have space, we occupy and the fourth dimension. What is the time? You think that instead of 50 years, for 80 years, and it changes to all the assumptions. So what I don't like so much is that there's recycling aspect, but not good on the earth. So I think on the earth life also has to be considered what kind of the use is already. This is part of it.
The specific one because it was based on a project where the client. So I think within our research, we try to push like different. Because we know that it is functional project. Client wants to have a more conservative measure within the industry practice. So they don't want to put it as 60. I agree with you that one of the strategies that how to kind of able to use each material for as much as possible. That's when the design for this assembly is how we handle the secondary material without the training or and there are a whole bunch of other discussions about the future. So in the EPP data, they probably 50 years. And I think this is 50. But also we have to rethink whether it is really 50 years. If somebody ever check it, then it stays with the same. It's a bit more about the materiality of the component. Next discussion. Continue that I think outlines the relevance of the whole NCA we can that only with material element level at least, and then of course this. Okay, thank you for the discussion. And we have we can talk about the third third contribution. Other questions?
Just one question, Julia. Who's going to clean that inside? This elements. There's a concept for that. Because I can imagine that after once in a while inside solo elements. This what we yeah.
I'm sorry, you're really, really badly. Maybe can you or
yeah, I try. I don't know which mic now works. Better like
a bit, I think, yes. Yeah.
Yeah, maybe then. So the question is to clean the thing. Clean inside. I mean, do you need to clean after certain white hollow elements, or do you think?
Exactly.
Yeah.
So the idea was to mount them into this substructure that I showed, and I'm not sure I can show it again. So initial idea of this retrofit approach was to use a related phase system where you can like clip the tiles after you assemble them. And also the idea was like we isolate this tile completely from like the inner space of the space. But when you mount them out, you can like remove temporary bottom and clean the nest. The regularity of cleaning is around like different for different species, but I think the most like once a year, so you don't need to touch them like too often. And this should have been possible. However, like because of other problems that to rotation, but because of the deformation, it was not so easy to mount them up. But it was only like first project in this direction. We tried it out, but yeah, that's why also we are looking into how can we prefabricate this element, because in conventional building, which is like so in the back, it is so hard to times and to clean them like at the high stability. Also, answering the questions. Well.
Thank you, Julia. Are there any questions? I think we wrap it up here. And big thanks. Thank you for presenters. Thank you all. For everyone in the room, we will have the
Thank you. Auch noch eine
Let's
Ja, aber eigentlich.
Ja.
Ja, es ist registriert. Das wird worden. Ja,
Just one, just two, just one, just. Go. Just one, just.
Hello, hello, hello. Can you hear us? Hello. Yeah, more or less pretty badly. I hope you can hear me properly.
Good. Yeah. That's it. That's enough. Okay. Okay, so in order that you hear us, hear me now?
Yeah, much better. Thank you.
Okay, so when we want to speak to the speakers, then we stand here. All right. So, I think we're still waiting for. So, Mirin, Yoga is with us from Austria, from the Institute for Renewable Energy. And that's already there. It says, I'm going with one you show, basically different connections and settings. We can hear you. And did you hear us? You can start.
So you were telling me to start?
Yes, that's what I did.
Thank you. I traveled hearing you. I'm sorry for that. But if you hear me, everything is. So thank you very much for listening today. I am going to present a research project that we carried out in rural research. It was inside the fusion grant call. This was a call for postdoctoral researchers where we work together with industry here in the area of the Sub-Zero. And basically, this facade industry and timber industry wanted to propose to the Italian market a novel facade system. And what we did from the research side was to encourage them to think about circularity. And that's why we ended up evaluating different connections and plugins for a prefabricated timber-based facade. And we assessed the materials reusability, water use, and global warming potential. So maybe in this audience, I don't need to explain so much about why we should go towards circularity in the facade industry. And we try to do this activity mostly for the industry, but well, in case we all know that if we want to keep on the 1.5 degree trajectory, we should really reduce our greenhouse gas emissions, and to do that, shrink the global material use and extraction is paramount. And that's why we should design facade systems that are not only effective from the assembly and construction side point of view, but also for the effective disassembly. The truth is, if that is, we go from the technical point of view to the literature, it's really difficult to find something about how we should design and propose these facades. And there is also a lack of practical experience to evaluate eventually how these activities could be performed, how effective it's really the disassembly where we think about these novel and the real reuse potential. So that's why we propose to assess different facade options regarding two sustainability parameters, that would be the water use and global warming emissions. And to do so, we propose the company to prototype the different solutions so that we could carry out experimental testing of assembly and disassembly activities. And then we use those outputs to perform a life cycle assessment for these two environmental parameters. So we took the information we got from the campaign is modeling, and these results are the one that I am going to present to you today. So based on the request of this timber company, we evaluated three possible cladding materials for a ventilated prefabricated timber-based multi-layer facade. Well, actually, the first two would be for ventilated option, the last one with no ventilation option. These three clients are the ones that are mostly requested by clients. And they wanted to learn more about which are the errors and the values related to this design and design choice. And then what we proposed was to not study just the state-of-the-art connections, that would be the staples, which they are currently using mostly due to cost effectiveness and fast application reasons. But we also wanted to test different options. So together with them, we came out with three alternative solutions that we wanted to test, which would be to substitute these staples by the screws, timber lanes, or geometrical assembly. So here you see all the possibilities we prototype and test. As I said, we carried out an experimental activity so that we could monitor the construction time and manufacture these four options. In this case, the experimental activity was done just for one cladding material. Let's say that the other three were just evaluated from the life cycle analysis. And what we did was to do these four prototypes, install them in our facilities in Iraq Outdoor Lab. And we also evaluated how easy would be one of the layers during the service life of this facade in perspective of enlarging the lifetime of these facades. And finally, we carried out these assembly activities. And again, here we monitor the quality of the materials and the construction time. So let's take a look to the results. What we got is that, of course, for the production, the samples are the fastest options. However, it really gets difficult if we want to do some removing activity or reinstalling activity during their service lives, and also from the disassembly of offline scenario, it was much more difficult than the other options. The screws increase a bit the production time, and again, even if it's pretty effective in maintenance activity, it took longer than the timber nails on geometrical assembly. Finally, these two most basic options, let's say, of connections among the layers, what it showed was that the timber nails were almost as fast as staples, that is the production time, because in the end, it's better to do it with that as in the staples, and therefore it was pretty similar from the production, but then it was surprisingly really easy to remove it. So it was a surprisingly positive outcome. Regarding the geometrical assembly, so no kind of nails or screws or staples at all. In this case, the production time was taking much more than in the other cases, also because it was pretty manual manufacturing what we did. And for the maintenance activity, it was really fast, maybe because when we proposed this option, we focused on this activity, and the disassembly was also really fast, as you are going to see, but surprisingly less effective from the time perspective regarding things. So I hope the video is going to work. And here you can see, hopefully, the disassembly activities of different facade options. I am not playing the video altogether because not the exact amount of people were involved in each activities. But as you see, both the timber nails and the geometry were really fast and easy, and it generate any kind of waste, whereas the timber frame prefabricated facade took a while, almost 1 hour to disassemble, and yeah, it generated a bit of waste. It was done, as you said, so also pretty manually in this case. With the two workers, the same ones that installed, they are used to install facades, but I thought they would have seen me as a crazy person asking them to disassembly, also trying to save material, not harming, but without being too time consuming this activity. And I must say they were really committed to the activity, so well, it was nice to start thinking out circularly also with workers of the factory. In case the video didn't work so much, but in any case, here you can see in the pictures of the material quality once that they were disassembled in the factory. As you see in the first picture, for the state of the art, create a bit of waste. And as the workers were able to try to save as much material as possible, they came up with a solution of cutting just the frame and well, the panels of closing from the outside and inside this timber frame were reduced in amount, but not completely for disposal. Instead, for the screws and the timber nails, only the holes remain, but it was pretty disassembly. And for the geometric assembly facade option, we had the panel in the original size and quality. And this is instead the state of the frame once that the disassembly was done. So in the case of the stable, the inner finishing plasterboard somehow attached to the staples in this assembly process. So with all and the quantification of the material that remained virgin, let's say, or that we could be reused, we took this information and we performed the life cycle analysis. And so, yeah, here you see materials that could be reused and the ones that were considered as for disposal. Yeah, regarding the conclusions of the prototyping and experimental tests, the panels designed for these assemblies were in better conditions once that they were disassembled and therefore potentially more reusable for a future lifetime, second lifetime. And the timber nails were fast assembly and disassembly connection. So it was a nice discovery. So taking now a fast look at the life cycle assessment results. What we first did was the comparison between this timber frame prefabricated facade solution, no cladding at all, and with different options that the industry wanted to offer to their clients. And what we got was surprising at first glance because you got that the non-ventilated facade with the plaster had less emissions rather than the one with the timber cladding. And as expected, the high pressure laminate panels had a substantial bigger impacts in the facade. So we also wanted to see if this was aligned with other benchmark facade technologies, and what we did was to take the calculations of Hildebrand and we adjusted it for a common value of 0.15. And as we see here, in general, these prefabricated facade timbers would have less global warming potential, but attention should be paid to increase with kind of high pressure laminated panels. As this result was a bit surprising, what we did was to normalize the lifespan, and we saw also part of our answer the question here because again This from the references we took, the lifespan of the plaster would be 10 years less than for the other prefabricated solutions. In all of them, the maintenance needed maintenance work were considered. So also in the case of the wood cladding, maintenance activity was modeled. And if we look at these values, then the outcomes were more aligned with what we expect. In this case, in comparison with the literature was a bit harder because they just consider a lifespan of 5 years. So this brings us the research question of, well, how can we accurately find lifespan as a and here you see the results from, again, from the global warming potential in case the no elements of the facade are reduced. And well, it's pretty clear the impact, high impact that the cladding has, but here it was also difficult to see the differences between the connections. So in order to, I will skip the results normalized because we already discussed about it. And so what we wanted was also to communicate industry partner why they should go for a connection that would allow a second life of the materials, and this was really hard if we were just looking at the first lifetime of the facade, and that's why we applied the credits of reusing materials that we detected during the experimental activities in this first life cycle. So what you see here in a brighter color, both red and gray would be for water use. It's the reduction of impacts that would have reusing these elements in a second life. So it's not the proper approach when looking at that element, because you should do it for the lifetime you are assessing. But this was the only way we found out to communicate the benefit of going for a silver connection rather than the current state-of-the-art connections. Here you can see a substantial reduction. Otherwise, it was difficult to communicate this to the industry partner. This is even it's even more substantial when looking at the cladding. So in this case, also if we can reuse completely the high pressure laminated claddings, maybe this high impacting material, if we find a way of reusing it second life, gets more attractive from the global warming potential point of view and compared to the other two options. So yeah, this project was technology and the way we found out to communicate the positive impacts and circularity if we go for reuse. So what we saw from the life cycle analysis is that the fixed systems, the layer can influence the results, and if we consider properly the amount of material that can be used. And this credit system was the one we selected to quantify these benefits and communicate them. Yeah, I will skip because I am running out of time. The limitation of the work we did was that when we disassembled everything, the materials were pretty new because there were just 2 days in our outdoor labs. So as future work, we would like to first gauge the components and then carry out the disassembly activities to make sure this is so easy and the materials are so reusable in a second life. And we also think that lower impact maintenance products should be identified, and the ones we use were affecting a lot to the global warming potential, and maybe we didn't look at the most innovative ones, so we should look further on it. Yeah, the reuse of materials, so far we just consider a possible reuse in the facade industry, but it also makes sense to look at other purposes which are not strictly facade. So either inner partitions or why not other sectors. Yeah, I would say this is all. Thank you.
So, round for the have two, and we questions.
Now for the room. We have another presenter online. Duhan Ato is talking about mapping and evaluating external wall materials of circularity, a case study of. Can you? We hear you.
Good afternoon, everyone. My name is Sita. Can you hear me?
Yes, we can hear.
I will share my screen. Everything's okay. You have my
In a presentable. Go switch to
now. Yes. Now I present my title, making an evaluation of raw materials. And my presentation consists of the parts. First of all, introduction, research question, methodology, and then research results, at the end, the conclusion. As the other speakers said that today we are faced with the fact that natural resources are decreasing and even decreasing. Despite this, the construction industry continues to use raw materials in most of the projects for various reasons, of course, but such as the ability to apply about the guarantee of quality and delivery. In conjunction with circular economy, circular design, and of course, circular construction, try to offer solutions to keep the materials in use before the end of their life. And the evidence of structured information about material flow and units in a systematic order. So in the transition of the sector to circular economy. To provide this structured information, material passport, further marking, and adequate information about this strategy, material passports on identifying materials and offering their information in order to consumption things. Undermining and material location, distribution, quantities of materials. Within the framework of topics mentioned, the research question, what are the building material types and reuse they obtained from the urban in party, engineering, urban engineering. And in parallel with the research question, mapping the construction of the raw and material and evaluating these materials in terms of the very compliance materials. Party district selected for the pilot area south. Party is one of the first settlements in Istanbul. The building is Istanbul and led the changing demographic. And 18,623 for 1999, the Great March. Therefore, units do not comply with the new build framework, which was informed
And according to Istanbul earthquake zones distribution map published by the environment, Fatih is located in the first degree earthquake zone. In scope of the research, the region which is located is excluded. There are a large number of urban buildings and buildings that need restoration are excluded from the city. And everyone has been affected from for 2009. And the building material published by Fatih. The figure is Fatih neighborhoods examine from Kudu. Exposed region in Congo. The four neighborhoods that have been mapped in detail are shown in orange. The reasons for choosing the four neighborhoods for detailed and visualized mapping are because they are the intersection of evaluation in spatial space and prepared by the body of sheet, which I below. The first one is according to building analysis, neighborhoods which have full condition of buildings. And the other one is neighborhoods that stand out in terms of many factors as a result of evaluation made prioritization approach. This study was carried out in 100 surveys and evaluation criteria. Basically, and on the other hand, let us set of material party of the geographic and also the information this is 2 months random check from documents and through physical observation. At the end, using certified evaluation criteria, the material stock was evaluated in terms of circularity and measurement structure for the selected neighborhood. And so how I create this circularity criteria list? In order to develop the circularity list, different approach the sources as a result of the review, and they were analyzed. One of them is Mustafa and Gibson. They divided the connections in and also evaluated them to 1 to 0. And from this classification, we rolled and nail and cement wall found in buildings. But you saw these were selected for the version. Also, there is another study. They evaluate the connections at center level with manual equipment and market center level and also from this separable connection. Separable connection found in the building. These are selected for the typical life expectancy and race condition of the materials are another side. These values were according to the material type determining buildings. And how I collect the data set of in party. In the geographical information occupied by there are labels for building. There are Turkish websites available there. By clicking on building label in one by the material data is counted, compiled, and presented in tables. And given in table 1, there are 6 classified masonry, wooden skeleton, reinforced concrete skeleton, steel skeleton, prefabricated and a mix of technical masonry and wooden skeleton. I skipped these quick because we will look the results and numbers later. Besides the construction type, the information about
exterior walls are tile, and 7 external walls for brick, stone, get ice, concrete, wooden, and mixed material brick and stone, and brick and stone are present. A plus 6 exterior walls, which material are painted plastic, stone or ceramic tiles, glass mosaic, which is especially and wooden siding, it is glass are presenting using circular technique the materials related both thermite and data collection were evaluated in terms of versatility, qualitative and quantitative evaluations were made. As a result of this numerical data collection, instruments were prepared for cornering flow. And so that the distribution of material type can be easily understood and information building can be seen. Immense external wall finishing materials were expressed color codes and external wall core materials. Construction types were based on magnetic blessing of we can see here. These are the general set results are the total of 30,000 assembled buildings in 4 neighborhoods. When we look at results in terms of construction type, the most visible type is reinforcement with 73.5%, and followed by the masonry 93.8%, and wooden ceramics 1.5%. When we look at the external core material type ratios, it has been determined that it is by far the most used material with 94.7%. Afterwards, it can be seen that brick and wooden are used. We encounter two materials that are very close to each other and experiment finishing filling using paint and are plaster with 0.5 and glass mosaic 0.4. They are the most used materials. Another materials are used at rates of 3.8 or ceramic tiles, and almost the same the wood. Now we are looking at the select neighborhoods. In addition to look at construction type, 94.6% of buildings in the was concrete structures. And in terms of external wall form material, brick was used in almost all buildings. Finally, the first two most used external walls are glass mosaic with 6 or paint and plaster with 25%. All of the use of reinforcement materials in the round of this system here, and it maintains the first rank with 77.5. Masonry with 21.5 can be said to be as another cost. Brick continues to be the most used format. It's 97. And in the finishing material, glass mosaic with 4.6, and its priority to paint and plaster with 57.4. And insignificantly, in addition, for concrete structure with a rate of 9.1. Masonry is seen 80% as a construction type. And both for material type, brick is the most seen again. And both finishing materials using grains are respectively glass mosaic and paint. And look at the construction type. The 87 points. The buildings are reinforced.
And also, almost 2% of field is in place already. Raw material type, almost all used in again. And non-finishing material used trains are expected to glass molding, and plaster, and stone. As a conclusion, brick and briquettes are the first to explore raw materials used most widely. However, when we consider that these two materials have several bonds and interactions, quality is not ready to reuse materials in case of iron. On the other hand, the use of wood, which has a high surface rate due to its ability to be examples, limited to approximately 1 million. And second, when we take the external materials data, paints and plaster and glass molding are not by the way, the base of wood siding, so every time PVC side and glass are the in conclusion, it is the framework of study as an answer to the research question. Although raw material data are positive in terms of regularity and low quality, not sufficient for partial verifying and the measurement of materials from in the current situation will not be expected in the use of the these are my preferences and thank you for
Thank you, Susan, for your presentation. Stay with us for the Q&A. We have another lecture in the room. We remain with the subject of life. And I think yes, that is your point of view. Go ahead. Title is Retrospective Facade Lifecycle. Lessons learned from case study, building nearing effect.
Well, first of all, good afternoon, everybody. Thank you for staying this long. And thank you for having us. My colleague and I are going to present an embodied carbon on a project that actually just finished. So the title is a bit outdated. This is a picture of the completed building. If you're ever in London, it's very nice, I think. But maybe I'm being a bit subjective. Nice. So Melissa in her earlier presentation already talked about each country's engagement towards reducing embodied carbon. In England, we like to do things slightly differently, of course, because we post-Brexit, but actually, I think overall the decisions are fairly similar. So we're ramping up our embodied carbon commitment so that by 2050 we hit the net zero target, which is very similar to what is currently going on in Europe. And we, particularly in London, have set specific targets for whole buildings in terms of embodied carbon, and then targeted more specific targets for facade. I won't go down the detail, but deep dive into the project, which actually was one of my first projects in London. It started in May 17. So at that time, I would say frankly that sustainability was really not at the forefront of our mind. But recently, it was completed in 2022. And during that very long period, we had a lot of time to think about what we could have done better. And that's why we've taken this opportunity to sort of go through and revisit our the decisions that we made at the time, and question ourselves as engineers. So this is just a slide to summarize what we've done as facade engineers, because I know some of you are probably not familiar with the obscure art of facade. But we looked at many different ways to potentially build what was like seemingly simple facade with bricks, precast, and punch windows. And we looked at different ways to potentially build it with either a prefabricated precast panel or a mix and match of different combinations of prefabrication and site installation. At the end of what we call stage 4, which is basically the end of design development in London, in England, we came up with a fairly robust, I'd like to say, design intent for the facade, and it was going to be built as an honest representation of the materials being used. So the intent was Henley brick, supported on masonry shelf angles, so fairly traditional, with the precast used as traditional lintel. So we decided to stay true to the architecture. But because the project was built in central London, there's a lot of logistical implications with actually having to scaffold the whole building and the implications around the surrounding. So to throw in a curveball, the contractor responsible for building this project decided to change completely our design and go for what we call a unitized facade. So it's an aluminium sort of prefabricated curtain wall system with an external skin of what we call GRC, which is glass fiber reinforced concrete, with a light specific brick slip. So it's actually a half brick that's been cut and effectively bonded to the concrete to create the appearance. This slide, I'm very fond of it because I think as a facade engineer who started on this project, it really reflects the journey, and I hope that it also reflects the journey of a lot of engineers in the construction industry. Just to put things in context, so basically in 2017, when we designed the building, we had no idea we didn't really look at embodied carbon or sustainability. We didn't have a metric at the time. But then when you look at like the time frame of the construction and actually consider the lifetime of different facade components, you can see that there's a lot of things that we could have done better. So here I'm reflecting the fact that, we started, like when the project was starting on site around 2020, we started having already questions about sustainability and embodied carbon. And we realized that actually there's a lot of problems with a unitized facade, because on this sort of diagram with linear economy, you can sort of see that in May 2022, when we completed the building, the facade would have been warranted for 12 years. But we know that because each component has different surface life, we can already project that most of the doors, like 10 years later, might have failed. 15 or 25 years later, you start having problems with your insulated glazing units, and then 30 years later, or 25 years later, your unitized facade is at the end of its life, whereas the whole frame, the structural frame, can still go for another 25 or 30 years. So there's really an interesting question for people who are working in the facade industry about how we can make sure that we design for a circular economy, but also how can we be held accountable for the design decisions that we made at the time. So as a company, we started doing a lot of our own calculation tools for assessing embodied carbon. We also have a structures team. We're doing a lot of work with Revit in interoperability, which is very interesting as well, to help architects develop, establish and evaluate their embodied carbon for different functions. And we're also doing that for facades. So now my colleague Javi is going to deep dive into the assessment that we did.
Thank you. So yeah, all of the framework and the tools that we were mentioning before are based on the same LCA ABCD modules. And so we start. This is a typical facade we analyzed. So there's a lot of typical cases with windows and balconies or opaque walls, but we just took that one, this one which has a window unit, an opaque brick pier, and a concrete scallop. So we could compare different scenarios. And the components, in order to be able to compare the two scenarios of a unitized and handling, because the whole exercise here was to actually analyze how the proposed handling brick facade is compared to the actual build solution. And we identify different components like the cladding, insulation, the frame, and also the all that substructure behind. And then we could have specific points to compare. And also another kind of highlight was that this design was much more highly developed because this was by a contractor. It was designed up to the screw and the membrane. So we just omitted the negligible components and focused on the main relevant elements of the design. So we start with the first A1 to A5 modules. And as you know, the A's refer to the manufacturing of the elements, of the components. And essentially, at the end, we were seeing that even if there's a subframe that has to have the GRC support and also more specific components, at the end, the hand lathe has a more drastic contribution because of the handling bricks and the precast. And also a particularity here is that the unitized, it was manufactured in Latvia. So everything was procured naturally, like the brickwork, the GRC, and the windows. It was assembled here in a factory, and then it traveled up to London, where it was installed on site. When we compare this to the hand-laid scenario, hand-laid solution, these will typically be procured nationally or even in Europe, but then it would be assembled on site. So we began to see these differences between both scenarios. And also, obviously, installation is a huge difference. We would expect the unitized, which was actually built to be using a crane and more machines to be assembled, and a hand lathe would require scaffold and more labor on site. So there is also a difference there. However, we were asking the design team, we were asking for feedback on the emissions due to installation. And right now there's no metric or there's no measurement to kind of say, oh, the installation accounts for this amount of carbon. So we went to the RICS and ISTRUCT guidance and based it on a cost, which gives you an equivalent emission for installation. And these are some images of the actual installation site. At the end, we see that this A1 to A5, the upfront A1 to A3, which is in the red, is really identical. Transportation, even if we saw that one had to travel really long from Latvia, and the other one would have been procured in London or nationally, it's actually negligible. Well, there is a difference, but it isn't as much as what happens in the A5. The A5, as we were saying, there's much more waste when you use a handling, when you go for a handling approach, because you have the cutouts on site, and it's much more, it's less controlled compared to the unitized, which is on a factory and is much more regulated. We go on to the B modules. B modules, for you to remember, it refers to the use phase of the facade. The facade is not automatic, so there's no emissions due to the automatization of motors. It's all manual operation. And we ask that as a maintenance people, the strategy to maintain and clean the facade. Basically, it's full cleaning of ceiling, so there's negligible emissions due to cleaning. But what's the intrinsic part was the P4 module. P4 module refers to replacement. And in here, what we did was a really exhaustive analysis and a categorization of primary components versus secondary components and how they would be replaced based on the durability and the materiality. So you can see here again, both cases, unitized versus handling. What you have to understand here is diunitized because it has an interlocking structure. There are some elements like the gaskets that are more compromised. So we would assume realistically that the whole frame and the glass are to be replaced at year 30. So we are basing this in a 60-year lifespan for the facade. So these elements in pink would be replaced year 30. They will be disinstalled, dismantled, go into a factory and refurbished. And this compared to the handling, this will require just replacement of the secondary components of the frame. And obviously the glass will be also replaced at the same year 30. And the main precast stays on site, it's just cleaned and maintained. And because of this assumption and this kind of educated guess, we start seeing how they unitize, even if it began in a slightly lower emission of carbon. Now it's doubled because of the whole replacement requirements at year 30. The Halley then is a bit better, just seeing this scope. And then we have the C module. C modules refers to the end of life. So what happens when the facade reaches an end of life? We also were discussing with the supply chain. There's little to no information on what's the mission for this dismantling or demolition. So we all base all of these in EPDs, information available from EPDs, or also the guidance from the rig side and iStruct team. For transportation, so this is end of life, dismantle. For transportation, we would assume everything is locally, it goes to a recycling site that is local or a wasting site that is local. So all of this informs the whole life cycle. And for the D module, as previously shown, we have this kind of pyramid in which we were assessing the main elements of the facade, like the bricks in concrete, the glass, and metal, and just assessing which scenario would be the most kind of realistic. For the bricks and concretes, it's ideal to reuse it, but we know that it really depends on the modularity of the facade. So it would rather go into a recovery, it would be kind of granulated and broken down, and maybe can be used as aggregates. For the glass, we are pushing a lot to recycling of glass. However, for an architectural purpose, with the realistic assumption is that it would go into a down cycle, namely to an insulation use. For metal, it would also go into a recycling facility. So all of these with objective of avoiding the landfill. So with these assumptions at the end, we get to these final results in which we have the unitized, unlaid, and because of all of the contributions and the deduction of the D module, which we must highlight that the D module is not something to subtract from the facade in the building itself, but it's something that is kind of envisioned to be within the construction system that would be almost equating both facades. And even if we at the beginning demonize a bit the unitize because it requires more elements and it's a bit more complicated, at the end, because of the whole recycling of metallic components, it would actually be even a bit better than the Halley system. Conclusions, which I already mentioned. And lessons learned. This is kind of a wrap up of the previous sessions, and we just have to say that for the design process, we have been also identifying some key coordination points we should have since the beginning, so like design charades or prioritizing design for this assembly. And we have also been noticing how now we are kind of specifying in our documents some embodied carbon limits, which were not really there back in the day. And this is for the whole cycle. We need to prioritize robust maintenance schemes, also have clear replacement scenarios, and we need a lot of infrastructure for reuse and recycling facilities to kind of remanufacture components. So thank you, that's basically it.
we have a Q&A. And we start with Milene, and you're still with us. Consider you. Milene, yes. Are there questions? I have one, or I have a couple. We have similar studies at our institute. Can you hear me, Miriam? I was wondering, did you look into the energy for the machines for the deconstruction? Did that as well?
Yeah, so you mean the construction or
The deconstruction.
manufacturing?
The deconstruction. Can you sample it?
Yeah, so it was mostly manual, as you saw in the video, because we had these two workers. So basically the only energy was the one of the train, the lorry train, and that's the only thing we took into account energy-wise for both installation and disinstallation. Well, it was pretty manual because it was prototyping also assembly-wise.
Yeah, I think when you look into the studies and what we also find is that the more machines you use, of course, the more you have. And it's always the question if you work with skilled labor, you account that, or you're not. You did not. The only thing that you mentioned here was that you said one person or two, right? Did not. I mean, you measured the time. That maybe also.
Yes, and here in the paper we presented conference and also in the Journal of Design and Engineering, we just shown the environmental analysis. For the company, we also did a life cycle cost analysis. So in that case, let's say that the manpower had also an impact in cost. So we took that into account for how much time and the number of people also into account the cost, which in the end should be somehow automatized way in the future, but they didn't have the machines. So when we asked also for the energy they were using, the factory was mostly, well, for the lighting, it is new machinery. It's not so far as really automatized and industrialized. It's there. Then we took into account that they have photovoltaics in their roof. So yeah. In the end, we asked for all that information and we end up not considering the lighting and heating the photovoltaic because so these results you saw are the ones because they weren't really directly related to manufacturing or this.
That's another chapter, yeah. The lighting. And since you showed my dissertation graphs, I was wondering how your position is on the end of life. So back then, I calculated that the production and the end of life would not do that again because the information is limited. When you look into what these numbers, you now included it plus you were evaluating the reuse and recycling potential. I would think one of it is enough. So it's either looking into the life cycle or looking into what can you do with it.
Yeah, so I don't know if I understood properly, but you were saying that maybe it was wiser just to not consider emissions related to the end of life.
Yes.
Yeah.
Because it's so,
Yeah,
there's so many uncertainties in it, and looking at the material pile and not so much at the construction itself, that I like your approach, looking into what is reusable and recyclable. Here we have an actual conclusion that is an action.
Yeah, it's a good point, and I will take that starting point for the next consideration. I think it's was the way of communicating. In this case, the credits were mostly referring to the low need of remanufacturing this in a second life. So you could see a much higher benefit. But yeah, I get to your point. Well, in the end, it's also true that we wanted to boost the producer. The end of life, even house of the end of life wasn't so big part of it. The most part of it was production. So in the end, I guess that if I go for that approach, they would say, well, whatever what we do is enough. But maybe adding also this as a result so that everything is accounted twice. Thank you so much. I will put it into practice.
You have another question from Jens Schneider?
Maybe another question is, when you show the picture, is it really intended that these panels will be reused as they are? Because I don't understand if they, at the end of life, get burned. Anyway, you can collect all the metal elements later. It's burned and it's easy to get them all at once. So is it really planned that these elements will be reused as afterwards?
So the intention would be to really reduce them, if not as a facade system in other uses that maybe they don't need to have such big performances. Of course, I know it's challenging, but also today we have the first presentations that if you maintain properly and properly, the elements can have much more lifetime. So of course, one limitation of this work is that okay, we just need we test mostly the assembly part and the detail, working or not. Then we should, to be sure if we can reuse them, we would really need to age these components out. So this is something we really want to do next, so that be sure that how these panels will look like in 50 years, where have already the full.
Thank you for your answer. I think we are all, it's very good that we're all working on the subject, and then some database for all these also same topic here. So are there questions for Zuhan? Zuhan, are you with us? Yes. A question. I was wondering, what will you do? So once you have it, what will you do with it? Once you have the material?
I couldn't hear you.
I said, what is the purpose? For what purpose do you collect all these data? What is the application of? Who will use the data?
Yeah.
I think the internet connection. Maybe we wait for her to come back, and in the meantime,
Do you have questions for them? I think, yeah. Listen.
Sharing the experience because we are looking at else. We find out like some of the data are actually like the image data. They're not so, or like not always reliable. In the case where you need your study, that you have to put a lot of and a lot of into because I'm just trying to understand like the difference, the availability of the data, Europe and UK, let's say, like as a comparison, how ready is our industry market together in this topic?
Yeah, I think you've raised a very good. And I know you mentioned 75 are circa, and I know we could have been championing like a third party checking the EPDs. And we've certainly had problems with that as well. The benefit here is that the facade was developed a system house who was helping involved. They produced a project specific unit test system. Fortunately, we weren't able to get enough data through the GRC, which is a bit of a, it's always a bit of a secret mix. They do and how they source the aggregate locally. That was a bit of a finger in the air. So, touched about on the waste issue and found that in a prefabrication construction mode, it's actually very well documented. Although now we have the new CWCC guidance, we had to make some judgments. You know, I mentioned brick slips that had to be cut in half. So we assumed that, yeah, about half, a third of the brick would be wasted. Use all the face kind of stuff. It's very much speculative.
Sorry if I, as we initially we want to also assess what the other. First, we didn't have to do it, but we didn't have really from our population, but actually it's also like before we can get
A very interesting part now that you said, you know, we're focusing on refurbishments and a very, well, one aspect that we think is of it. Having someone or a service to go in and then check that you have, see what you can use or recycle. Very interesting. Research.
I'm not an expert in that topic, but I find it interesting your presentation. And my question, just by the very final phase of construction, this question of life cycle is triggered by some concerns. You mentioned the maintenance was one concern regarding the materials, and also maybe you told that it's good to know for the coming construction about guide on missions. What was the main motivation and why was that day? Like at the very final phase of because the design is really like starting designing and why that like this one like this.
This is yes, it works. Very interesting question. So it's actually based in central London, and design at the time was relying on, well, I said it was honoring the intent of the architect to use bricks and the precast. It was actually inducing a lot of sequencing work, because you then have to, so in terms of the realm of scaffolding, which is actually something very interesting, you have to do one level, puts the backing structure between the bricks and the windows. And then because the precast element is too heavy, you come down with the scaffold, the precast. And then you have to go back up with the brick. So it was this whole idea of construction sequencing was very complicated. The fact that you were in central London meant you don't have enough storage space as well. So all the brickwork had to be stored somewhere. It just wasn't possible, you know. So the bond between the brick is cement mortar, these massive silos, and just sort of created this whole logistical nightmare. And then COVID hits, so there was the whole idea of we want less people on site. We wanted to build with better quality. Let's do it. There's lots of yeah.
coffee break. Come on in. All right, now we have on the top campus. We have our first speaker, Javier Fuentes. Javier, nice to have you here. It is called Recode Vicar, and Javier is from AIT Karlsruhe. Please stay online, and we will do a session at the end of this. You have to unmute yourself, Javier, and
yeah, sorry.
Share your screen.
Thank you. Okay. 1 second. Yeah, can you see my screen now?
Yes, perfect.
Okay, thank you. Well, yeah, as I said, my name is Javier Fuentes. I am an architect, civil engineer, and I'm working for digital design and fabrication in Karlsruhe Institute of Technology. And we are a team formed by very different backgrounds. We have engineers, architects, also people related with the world of arts. With our team actually, but I'm a professor or Stoster. We are currently growing a lot. The professional like 1.5 years ago was formed. So we are now under developing, really fast development. Our professional team is basically studies how to work with natural composites, work with fast raw material, we work with flats. All of them are plant-based, local or earth-based materials that have low carbon impact. And we apply different digital design and fabrication techniques to transform those materials and be able to produce building elements. Building elements that later can be, the life cycle of our building can finish, could be reused, could be recycled to other purposes. I am going to explain more with the field that we are working in four different topics. We are going to start with materiality. Well, we have, as I said, we understand that our resource material. This is the place where we are going to grab our building elements. We are going to transform them. We are going to work with them and develop different something. Those raw materials requires a process to be able to use it. In this case, bottles of willow. We have to first of all grab the willow, store them, it's dry to accepted conditions. And then later, to be able to work with the willow, for example, we need to add humidity into humid those willows. At the very beginning, we started with the willow to basically a chemical. Your pictures, we introduce the willow to water, and after 3 weeks, more or less, the willow was able to work with it. But in this process, we found a much faster process, which is actually in the willow. We found these tubes and this steaming machine. Steaming the willow, you can have the willow prepared like 7-8 hours or less. So we have reduced quite a lot this time. Basically, this is the material that we are working with right now. Natural materials, the willow, okay, we mix it with another material, earth, how they can be combined together. We try to the capacity and all the properties of each one of the materials. In this case, willow is working in traction, in tension, sorry, and the earth is working in compression as a concrete slab is doing basically natural one with a really low carbon impact. material. This is about materiality, about the design. We are trying to figure out how to define the expression of this material, how those building components that we are working with should look like. If we are building with Lilo, we are in this process of figuring out how has to be the final outlook of these elements. As you can see here, some tests that we were doing with our process. And here, for example, is one of the demonstrators that we have built last year. Yes, you can see here that it's based out of different components that have some interlocking logic. And yeah, we try to find ways to combine them to achieve certain programs, to achieve whatever requirements is established. Here you can see, for example, pictures of each one of those modules. Each module is different. Each module has its own, let's say, its own properties. To be able to work like algorithms, design technology. This is the whole field that we are applying in our. Here also for us to have campus is very important because we were able to develop, for example, in this case, connection. We were able to study how will be the connection between those components, two different components. In this case, we produce here a wood plate inside the component, inside the window structure, and this allow us to join a component that before you couldn't do it that way. We are still, develop little by little, but we try always to improve on every project that we are doing. And here you can see those are the those are the modules that I have been talking about, a mixture of below and earth. We study each module and we add earth or below heating pattern where it's required. Here are some of the projects that we have done. On the left is our first project that we developed here in our faculty in Karlsruhe. It was a very big column that to assemble this column we have to do it through the of the faculty because there was no other way to be able to feed this component really manually anyway at this time. In the center you can see another project here in Karlsruhe. And on their slide, you can see the model that the project that we developed for Balkan. Also, we don't work alone in our profession. We work also, we collaborate with another profession, kind of a structure, it's the professorship of Ricardo Lamagna. And they basically help us with all the development of structure, how should be those within patterns in this image. Example, you can do it like a text, one being down with Willow. We calculate where we should add more within pattern, where the pattern should be more dense to resist the exterior conditions. About fabrication, well, as I have said, we are very interdisciplinary our team that is currently developing tailor-made machines or to build those components, allow us to be much faster, much reliable, and of course, using all the power of the computer, all the technology that we have in our hand, we can much better interlock those components. Of course, we have to match the design. Here a picture of one of the modules with the weaving pattern for this machine to translate all these designs, all these different components into a logic that a machine code basically. Here are some pictures. For example, here on the video showing here, you can see the weaving machine working in was Pop-up campus. Here on the left is the same we have weaving machine producing these weaving patterns. We also use algorithms to study how this component should look like. We use different technologies, AR, VR, or algorithms to produce automatically with those weaving patterns. And for us, it's also very important teaching because we all develop at the same time features and they are always combined, they are always, we transfer elements from one side to the other. So our students in PID, we show them how to work with, we start working with clay, we come working with techniques, with the hands. We did also with the widow, We produce, for example, a clay model, then we scan this clay model, we produce a point cloud, and we teach them how to 3D model, we teach them also the application techniques, in this case, 3D printer, and also heat technology. Also being quite important for them to achieve better job position. And also, of course, algorithms, like how to use grasshopper coding, but this is in the basis of our research also. And here you can see the demonstrator for pop-up campus that we did. It was made out of components, different pieces, joined together. Here also a video with the. Yep. So that's it. Thank you so much. Hope you like it.
Thank you very much. Yeah, very interesting. We come to discussion and later in the Q&A session. Please stay tuned. I'm sure there will be some questions. So now we come next speaker, Christina Sonborn from University of Wuppertal, presenting online. The talk is called Re-Narrative. Christina, are you? Yeah, perfect. Because you understand us because we the problem that not the same mic that YouTube. Okay.
Yeah, hi everyone. It's quite difficult to understand you, but I think I think. And maybe you can give me a feedback. You can see my screen.
Yes, perfect.
Okay, so maybe like full screen. Yeah, I think see the full screen as well. So yeah, hello everyone. People. I didn't understand this, but yeah, maybe talk about this later. And I would like to present the results of a very, very short research. And we did this summer. And it was part of a format called Secret. It was really very short. But although it was that short, there were many activities such as the pop-up we that festival. And yeah, first I can say that I work at the University of Wuppertal at the time, and she wrote the Atlas for work. And we cooperate for this project with a Danish architect called Stern Nielsen and Frank. He was in Germany in Wuppertal because of the corona, and so he joined. And workshop was kind of a journey of confrontation of previous subjects. The subjects with the acceptance of agreement with friends. And our project was dedicated to reuse material and according to the motto of and 150 years ago, the construction system had a small effect on the environment. Buildings also reach the requirements for in new buildings or so the disposal problem did not give examples of the Japanese visualize the use of local and regional materials. And today, in many parts of the world, we do not build in areas like which they were for building cities. There's a question on those deal with the local materials materials now. I don't go with urban mining. And the greenhouse, new construction, new building and new materials. And so designing with renewed materials implies dealing with unpredictable and random dimensions with the colors. Design process. Difficult part of it is reversed. Material or component, whereas new materials are not given design. Okay? It will go into it. Quality of plants. Many accessible objects experience as balance that are simple and surprisingly different. And on a scale between boredom, radicalism, architectural aesthetics based on reuse and potential to create such a balance. So, as I mentioned, we worked with Bernice that workshop, and they did or he do research before already and it deals with more food. They created a beautiful workout, and that part they with concrete ceiling. Next picture you can see how they use tiles. And visualize it after that, which appears now phenomenal, I think. And what they did as well is they made an overview of connecting methods and describe them for use them as motives in their designs. So, and if they plan to use materials, they think about how to disrepair or just at the end of the technical motive. And our project was and the and they were and all we had for week and other years. And first of all, in translation, first, like waste materials and unused materials, and they the material catalog like does, and it contains a photo, lots of information to the condition. And here it is an overtime, and we did it at summer and on the outside area. And yeah, you can see there were different groups of students created by students each group, and the available components represented a random waste building with mostly small dimensions. Or they do not think they are predictable. And yeah, these conditions constitute a field of coincidence, which is first programmed from open-minded creative design process. And out of a chaos, here in the background, well-defined solutions will emerge of semantic level. And now I want to show you the lines. And the first one is thinking that deals with materials such as which are often glued in conventional construction. And they put them into the construction form of a key break. And the only thing that holds the materials weight of it. There's a space in the construction, and through overlapping, they hold each. I think after this brick slips, after 10 brick slips or something, there's a screw which holds wheels. And you can imagine that the construction isn't only wooden stripes, like also use broken material. The next one, brick sticks. We often see them in Germany, and they cut them on the long side with a 1 centimeter deep groove, and they deal with different things which were in Wuppertal, and they tried to backsplit the switch, and did a lot of samples, and I think it was very difficult for them because they also used waste material as a combining material, like plastic. And you can imagine something else like steel rope. And the last one is called softness, and it deals with old fabrics, greenhouse here, like in red and silver, and they were used as leading. And besides that, they used old parquet, which wasn't used in other flooring. Broken, and they used this as a construction material with the fabric they and what you see here, so they did a different type with that silver base and with leaves. So what you can see here is that although it is dirty and overgrown with moss, and there are lots of different holes in it, it can get a new setting. Like visual as a student, and I think imagine interesting the university. So I hope radiation will become the new normal for all of us, and curious how it will.
Thank you, Christina, for this amazing talk. We will have one other session, and then we will go to the Q&A session. So please stay online for questions later. Okay. Very good. So now we come to the last one in this. It's Saki Aziz. from UDK and aviation. I mean that UDK University of. And his talk is called Minimal Mineral.
Thank you so much. I think I can just start. Thank you first of all for that. This project is not really, I think, under the framework of PowerSKIN, so it's not a facade topic. Basically, it's more looking at construction systems, looking especially at slab structures. I think it's still could be good thing. So please let me know if you should not see my video presentation, which is the presentation. It's like a PhD student that we do in Berlin under Professor Carlo, under my PhD thesis called Minimal Mineral. Not quite sometimes. And it's basically an investigation of a digital product for function integrated and resource saving mineral structural elements and efficient software. And I will try to make it a bit brief. It kind of needs too much widening what challenges we are facing, but I think we are all kind of in the topic, so we know what challenges lie in front of us and why we need to create maybe more that processes are more sustainable. Basically, having huge issues at the construction space called CO2 emissions, and one of the predominant construction systems that we're looking for reinforced concrete. And then, of course, if you look at the statistics of how much CO2 emissions are caused by the generation or creation of raw material of concrete and steel production, quite significant. And another feature that sometimes is overseen is that we don't always need to put so much mass into place, or we have an potential to optimize basically how much material is used to create constructions. And one interesting thing is that every person on this floor would live like the average human citizen. What you for us to sustain our life. And this, of course, also translates to the way that we building stock. So 60% of buildings that will be needed by 2050 need to be constructed. So it is maybe not bad exactly such interesting ideas, at least how solutions could be shaped to foster such ideas. Having said that, what we wanted to do in the beginning is understand what we're looking at. And we're concentrated on the building type that can found all over the world space, and wanted to create a schematic design, parametric design of typical office space, which is not like a nice design, but utilizes the idea that everything is trying to be systemized. So you have a grid that is basically overlaid. You have a 3D involvement of the space that you would need. You have usually a post-view facade that is basically put on it without saying anything to them. Also, kind of typical limitations that such facades have. But what we were really interested in is that the reaching and how much embodied carbon each of the holds. This is a study not done by us, a very famous one. And the study is shown, which kind of is a bit obvious, that of course the horizontal structural elements, for example slabs, are comprised the most material, but also the most embodied carbon that is allocated in them. So we saw a great potential target exactly this and try to optimize in a way or with an idea that we're putting here. You look at one unit itself, wanted to show how actually the construction system works. So basically, you do a lot of formworking, create a slab structure, you have to assemble it, and what we saw is that you have a huge effort in manual labor and costs to actually create those formwork. So almost half of the price is allocated to just creating the formwork and then basically also assembling it. And based on this very primitive idea of formwork, we then lay in the reinforcement, which is the, and then you pour it into the concrete on site. And the idea was to use technologies such as additive manufacturing to minimize the of formwork, and hence to also optimize the way that the slab is maybe geometrically shaped reduce the overall instrument concrete that is also coming from two angles, trying to optimize safe material and also avoid carbon. That was the raw construction. So if you look at the office fit out, we have a floor, and then we have needed for ventilations, and these also sometimes cause noise pollution with the cuts that are there. Okay. This still from myself. So what you have is basically a recombinant acoustic ceilings, and the problem with this is with each layer that comes into it, you have a huge package at the end, and we wanted to target exactly those two ideas. That first we want to optimize the slab construction itself, but also implement the thermal heat transfer and sound absorption and integrate it into the slab that we want to create, in order to slim down the package overall and to have a more intelligent and multifunctional slab construction. This is the premise of my PhD, and now I want to show you how we try to solve it on demonstrators so far. Basically, I mean, in slab construction systems, we are not in the beginning of it. We are standing on the shoulders of giants. In the past, a lot of interesting projects have been developed. And what I found very interesting always is that, especially the ceiling design, this always has a very interesting aesthetic value. But in order to create this aesthetic value, you also have to have the state-of-the-art ingenuity of engineers, because we need to solve problems to make something happen right here in construction. McGarry is a very good example, but also Navi is a really amazing example. Also, we need to create aesthetics supplemented with engineering. So we thought, let's have a look at load construction systems and try to evaluate them on different criteria. Here, doing an LCA analysis for the building construction systems and basically trying to create algorithmic scripts that can generate those systems that in order to investigate. What we saw or found interesting is to concentrate on two ideas. Basically, unidirectional spanning construction, such as the cap ceiling, that's always utilized in one direction. Or you have systems that are utilized or function in two directions. That would be a bubble slab. We thought this idea interesting and wanted to explore both of them. So we did another evaluation and saw that not only the area related mass is relatively good compared to the big brother, which is the reinforced slab, but also the sound insulation is something that's already playing out on hard. That's something we wanted to concentrate on. And the first demonstrator that I want to show to you is on the capsuling structure, and this was actually a part of our campus that we did this year as a demonstrator, looking at cap structures, utilizing robotic fabrication to revitalize this construction system. That's because we saw that the craftsmen for creating these structures are diminishing. The knowledge is being lost. We wanted to try to bring it back in a way automated and try to kind of archive into new ways of making space, which is, for instance, robotic fabrication. So Kappa Plus, again, is this structure that is spreading in one direction. And we wanted to explore, of course, robotic fabrication. But we found interesting that the overall idea is to just assembly bricks. And for this, we wanted to use two types of bricks. One is recycled, basically, that you can find on mass here in Germany, but also creating new modules, new brick types that are really capable of absorbing sound. The system that we will show you in a second. So this was the premise, and then of course you would need to automate it and put a digital process chain. We want to use robotics. It shows the idea that with algorithmic design, you can pretty much build all the parameters. I have art and install different patterns, obviously, to store or see. And once you have that in place, then you create a fabrication hub. So that's what we did. in part of the pop-up campus, we tried to do it here in Berlin. Create a very small, very low tech unit to create smaller sections of a capsule that can actually be constructed to larger sequence. Right, there's movable beams that you can see. So once the 7 rows are laid, move them, and then the next sequence started. And this is our little hub that we built for now. Basically, a robot, small one, Wi-Fi, just be able to grab, pick and place bricks, go to a water station to precisely get the water it needs. That standpoint that we work, and then after each other, just assemble the way that we can pretty much define ourselves. There was like programming that we can utilize. I think that there are there are a lot of options, let's say, at least. There were a lot of trial and errors that we do, a lot of manual work to get the system right. But at the end, we were kind of surprised that it was a very robust system and you could actually generate sections of that and then create a large piece at the end. We have 2 reading stations, as you can see here. This is still prototypical. Here in the next year, we want to put in our additive manufactured acoustic bricks. Right now, they are not. It's just a different type of brick. On the other side, you can see the recycled bricks. And then together, we can create more complex patterns of how we arrange them. The idea that I was talking about with the acoustic bricks is to find that you can, or your hope was to calibrate exactly how much sound you want to absorb and shape the bricks just by the means of geometry to absorb them using the idea of hand monsters, which we will be looking at in a second. Precisely, and it's basically just void cavities like bottles, and as you know, if a bottle has different volumes of water in it, a different sound comes out. And that's the whole idea. You can calibrate it quite precisely to absorb sound, absorb, and we create this whole digital process to create them. And right now we are looking to create these bricks using clay as a material, which is still in works. Let's see how that goes next year. A part of that, so we built the demonstrator. We also went to the Power Campus in Aachen and built a other prototype, which only deployed manual craft from experts. It was quite interesting to see how they actually, with the skilled knowledge, built the structure. There was a lot of discussion and a lot of meetings to understand how we could use this knowledge integrated into the robotics setup that we have in Berlin. Looking at their techniques, how they put the water out, how much pressure is used to basically put them into the place, and what else can be utilized and basically brought back to this new kind of construction sequence using technologies. So we did the test. We obviously did the image where we all stand on the thing to see if it breaks or not. Some of us we are not that sure, so let's see. Let's look off those 20 beam. This is a different system. But we just what we can do a hybrid system of what it can be used. Basically capturing that is elements to bring or pull them together, mainly also for transportation purposes. Comparing, of course, that to the demonstrator that was built by the robot. I know the time is a bit tight. I have like 5 minutes, I guess. I will try to just give you a few impressions on the demonstrator and after that, or basically the demonstrator that looks into a 2-dimensional spanning system. For that, we're using 2-way joysticks. That's what is how it's called. It utilizes homework properties that you saw there. Plastic homework bodies, you put them in place, reinforcement in there, and then you need to disassemble them. And then what you have is a stuff that has those kind of offerings and has, of course, less material that's in there. There's a very, very old kind of technique. I mean, Pantheon is a good example of such a system. The issue, of course, with that is as soon as you go away from the standardized module size of those homework bodies, and you want to explore a bit more of interesting geometry, such as Navi, for instance, in Navi. Those where he was looking at the force flow in the slab, depending on the positioning of the anchors, etc. And this force flow actually kind of gives an indication of how the forces are actually in the slab. And based on this kind of notion, create a different kind of pattern to describe the grid structure. How they can basically say that in this form, the slab is also structurally independent to grid, but carries them down a bit. But if you imagine that, so what we did, we analyzed it obviously, and using a grid system to automate this process in order to create a pattern. And the idea was to then create this slab using formwork bodies. Issue is that if you use plastic formwork bodies with those kind of exotic shapes, it is going to be very cost intensive. And we don't want that actually. So because you have this plastic formworks, you do not use them again because you don't need the shape again. But to disassemble them, you would still have this plastic formwork bodies, and you would need to basically throw them away. So it's not very sustainable in my opinion. Basic concept. The idea was then, this is also an idea that has been explored by different people. One of them is Team Graz, which we are working with very closely with Professor Peter Stephans and his team. And we said, okay, then let's look at exactly those formwork bodies and try to create again a process chain to take a boundary curve, extrude it, design it a bit, and also have algorithms in place to check if the overhangs can be actually graded, correct them. What we also are using is it's a fresh concrete that we pour on it, actually stays intact. And if it not, we can adjust it. And once the geometry is fine-tuned for each code that we have here, with the G code, basically the print part of the for the machine, and then you can again create shapes as you can see here in a very fast and precise manner. Actually, we did about 40 pieces in 6 hours, which was very surprising. So, I mean, this is not groundbreakingly new. It's just good that we could implement it for ourselves. But what my PhD is actually looking into more precisely is to integrate more intelligence just by the means of geometry into such elements like the formwork bodies. So we're going back into the space, and we're interested to activate it as a thermal heat exchanger, a slab, but also as an acoustic absorber. So this is two things we want to tackle, integrate. And the one thing that we really went into the rabbit hole was we had the acoustic absorption qualities that we could activate using, again, this idea of Erdmassensatoren. But this time we went really collaborating with the Department of Audio Communication, and together with them, again, look at the overall idea of Erdmassensatoren, which basically describes two volumes, right? The bottleneck and the body itself. Depending on the volume distribution of them, they absorb differently. You can also chain them together as a linear structure. And we created a workflow using graph software, COMSOL, which is the FDS program, to analyze these absorption qualities. And just played around with the geometry and volumes to identify exactly when a certain frequency range is absorbed. In our case, between 200,000, even less, but I will not go into the depth. I have a different podcast and just analyzing it. And what we were kind of glad and achieve at least that we could, for each geometric modification that we do, the precise values of how this would be translated into the bottom result that we explore it. And based on this,
we're running a bit out of time. You have to speed up a little bit because.
Perfect. Yeah. I'm almost done. So basically, we looked at created physical prototypes, looked at that, evaluated them, that includes to verify that those values are correct, and the overlap was quite significant, so it means it works. And then using this idea, we basically created or implemented those formwork bodies, creating a spatially configured acoustic absorber that can be very complex and have different zones, etc. They created this demonstrator that I just want to fly through right now, which is this guy. And this system now is just a demonstrator, but we are happy to now if you actually build a smaller seating structure in a interior space using this system. And this is basically more or less comprising my PhD the type of material. And yeah, if the time is done, then I'm finished. Thank you so much. I'm looking forward to it.
All right, thank you. Very good. So we have some time for the Q&A. And the first presentation we had in this session was by Javier about the recode figure. And who's doing a question? So Javier. We have started on Javier. When you assemble these elements, potentially this the wood or the little elements that you use, they are still relatively fresh, because you said you first dry them and so on. And what is about the change of the material properties over time when they are in use? Is there any issue that this wood gets more brittle and then later, you know, just by some loads, the whole thing collapses because it's brittle then? Or is this not an issue?
Actually, this is not an issue. The problem that we are facing is under manufacturing. So when we work, for example, depending on the material that we are working with, if we are working with flax, for example, we are using resins. We need to use resins to get the fibers of the flax bound together. But in this case that I have some, the projects are done with willow. For willow, the most important thing is for manufacturing, you need to have the willow steamed, because if not, it's too rigid and the material doesn't allow to bend it. And we are basically working bending the material. I didn't show in the presentation, but we did some tests with the willow. Actually, the stress capacity of the material is really, really good. We, until the moment, we haven't faced any problem that, because we only estimate for the fabrication. Then once it is, once the willow is done with the pattern are done, we let them dry again, like 2 days, and then we add the earth. The earth also has, is bounded, I mean, we follow complex process with the earth actually, adding some additives and water also. And we put it inside the willow basically to absorb where it's needed, to absorb the compression forces. And yeah, after that also requires like 2 days more to get everything right, and then we get those components at assembly on site. Sometimes the air we put it directly on site if the component, for example, is very heavy. I don't know if you can see my screen. Can I show the screen on?
Yeah, maybe we have just share it, please. You don't see it now. Now it's.
Yeah, here we go. For example, in this project that we did, the earth pieces were really heavy, are those ones. Okay, so as you can see that in the modules, let me share the screen too. In the modules, we add like some pieces to hang the components and install it on site. We did it in a factory which was really close to the place, but we are doing another one very similar. We are actually building those components directly on site. We built like the willow in the factory, which act also as a formwork, and then we add the earth on site directly, because if not, it's like 150 kilos, 200 kilos per component. So it's much easier to handle them directly on site.
Very good. And how fast does this grow, the willow? How many centimeters per month? I mean, how fast?
How many? We are basically we are getting the willow. We are not producing the willow. We get them from local suppliers here in Germany, and actually we have to get it every year. But this is actually a very good question, because working with natural materials, for example, we were expecting to do a pavilion with flax, and we have to change radically the material. And it happened 1 month ago. We have been 6 months designing the pavilion, and 1 month all the suppliers cancel all the shipping processes because this year, due the climate conditions that we are facing, for example, flax is mainly produced in the north of France, south of Belgium, due to the conditions of the summer that was very warm. There were not enough material. So we are. I mean, it's very interesting this field that you have to adapt yourself to the natural processes that you don't have totally, let's say, unlimited resources. For the willow, there is actually no problem. I can tell you, I honestly don't know how much is growing per week in the plant, but actually we are not facing this problem because willow is in many places around Europe. It's not like flax. Only placed in one local place.
Okay, thank you.
You're welcome.
We have the presentation by Christina Sonnenborn on the reader rate. Just a question from my side. You showed that you have different knitting technologies historically, the witch, I don't remember the other names. Which type was the most stable for assembly? Maybe you could put up your screen.
Yeah. Right, it was the first one was the zigzag bit. The students showed that. And I think on that part they used the backstitch. So you have the overlapping from the brick slit. And I think it was more because of the short time that they have to produce lots of this, and that's why they use the backstitch for the mock-up. But I think they weren't at that point where they could say this one was the most stable one.
Thank you for the. Do you think is that for failing it? Prototyped it? Can you hear me fine? Yeah. I think this is the mic. You should hear me now, right? I was wondering about the potential to upscale it. You are now working on a prototype scale, and what would be the next step? Is it transferable like it is in a bigger scale, or would that be a different kind of study?
I think we have to upscale it because there's so much potential in it, and the students collected lots of material very easily around Wuppertal. They didn't have to search for it very long, and it was only like really waste material on places or something, and lots of material was used on construction sites. So we have the courses, and it is very important, I think, to test how to design with materials that are given. And yeah, it's maybe a pity also that we only had 3 days for the workshop and 2 days for presentation and organization. And yeah, I think you could also implement in a more stepwise, but in more steps in the workshop. So they were very fast in choosing one material, testing a few hours, and then bringing it on to the customer. And we take more time to understand the material and try out more forms of material.
Thank you.
I think 30 was in Austria and did this project 1 year ago. There they had 3 weeks. So if it's in that scale, like a little student project, you should also have 3 weeks minimum.
And now questions to Sakib Aziz on the material. You have there. Not here, but maybe I have one, Sakib. I don't understand in the slab solution that you have. I can imagine that fire protection is a big issue because typically that type of slabs, like you showed the Nervi and so on, this is relatively straightforward. But if you now have the very large openings that you put, isn't there an issue with the fire resistance of your slab?
So that's an excellent question. That is one of the topics that we need to get next. It's right now not adequately sorted out. We have to say in the beginning. Basically, the system is still looking at a structure that is already existing, bubble slabs. So fire protection, especially for those construction systems, have already been investigated. The one thing that we hope is to explore a bit more the material that we use to actually break those wall bodies and validate their values regarding fire protection. But this is exactly something that we would need to now test for physical prototypes and investigate and actually create the data to validate that. So I hope that using a construction system that already exists is really and optimizing or playing with the parameters of the material that we use, and of course on the properties of the geometry, that this could be comparable to at least the bottom slab structure in the example that we showed. But right now I cannot give more information. So that is an excellent question, but hopefully we'll have that quantified next year.
All right. So yes. Okay, though, then thanks everybody for joining us and taking time to say fascinating stuff. We will have a discussion now. We go to the room number 1 here, and you can join, of course, also online. I think we have this room now. And I wish all of you a good evening and have a good time. Thank you.